Okay, so we're going to start off with a quotation by Heaviside here. Heaviside had an interesting way of starting off his chapters in electrical engineering by telling little stories. So here we have a story. The following story is true. There was a little boy and his father said, "Do try to be like other people. Don't frown." And he tried and tried but could not. So his father beat him with a strap and then he was eaten by the lions. Reader, if young, take warning. By his sad life and death, for though it may be an honor to be different from other people, if Carlyle's dictum about the 30 million still be true, yet other people do not like it. So if you are different, you had better hide it and pretend to be solemn and wooden-headed until you make your fortune. For most wood-headed people worship money, and really I do not see what else they can do. If particularly you are going to write a book, remember to be wooden-headed. So be rigorous, that will cover a multitude of sins, and do not frown. There is a time for all things, for shouting, for gentle speaking, for silence, for washing of pots and pans, and the writing of books. Now let the pots and pans go black, and let's set to work. It's hard to make a beginning, but now it must be done. So this is where we begin, with the advice of Hall of Heaviside. So we go right back to the origins of science, which bring us to two people, Plato and Aristotle. But first, let's go back to Steinmetz. This is the guy who basically we're talking about. He invented the mathematics that allowed a picture and an engineerability of electricity that was beyond anything that any of the great mathematicians or scientists or anybody from that era could do. This is about 1900. And then in our next shot, this is the other subject of our talk, is electricity in its wild, pure form. You're looking at about 100-foot long, 440,000 volt, 1,000 ampere electrical discharge that just doesn't want to go away but continues to grow. These are the things that the electrical power industry was almost brought to its knees on in trying to tap or prevent these type of situations from happening in the electrical system, and Steinmetz was the one that figured it out. Okay, the next shot. Okay, now Mr. Whittaker wrote a book called Theories of Ether and Electricity, or the historical representation of the theories of ether and electricity that covers all the scientific work in electricity. It's about a 3-volume set of about 1,500 pages. And if anybody wants to see where all of these ideas came from about the ether and about light and about relativity and quantum, this is the guy that cataloged the whole thing in a way that is just absolutely mind-boggling. Right down to the finest detail. You can go through all of Faraday's experiments and Maxwell's experiments and make your own decision from them, because he doesn't make a decision for you. He just simply outlines the history. So you don't have to redo all the experiments of the past 200 or 300 years. So go to the next shot. Okay, now we have Plato. So our method of thinking comes from two people, Plato, and then we have following him, we have Aristotle. So Plato's thinking was to produce schemes more or less independent of existence on the basis of all being, and they were totalitarian in nature. Where Aristotle is the systematic experience of the surrounding universe, truth attained progressively through the work of individual efforts. Now, Oliver Heaviside breaks this down a little further in the concept of natural philosophy. All of these people, Heaviside, Maxwell, Thomson, everybody that we're going to be talking about consider themselves a natural philosopher. It's a mode of thinking that doesn't really exist anymore today. Now, Heaviside broke the natural philosophy down into two terms, those of the vitalists, which dealt with the living world, and that of the materialists, which dealt with the non-living world, which of course is us as electrical engineers. Now we can find the basic beginnings of science out of Aristotle's thought, but it had to be modified by an English Franciscan friar by the name of Ockham in 1350. He broke tradition with medieval thinking around 1350 and can be called the father of modern science. His line of reasoning led to Copernicus, then Galileo and Kepler. The mode of thinking was now how instead of why. Descartes in the 1600s continued the line of reasoning and developed the first concept of the ether, which is the most important concept in dealing with electricity. Descartes regarded a metaphysics beyond the physical. He called it the last part to be studied, as it is necessary to have previous knowledge of many things. The study of electricity, considering the electric phenomenon as non-physical, is hereby, by Descartes' reasoning, a metaphysical and not a physical study. And this is the center of the whole problem. Electricity is not a place for physicists. Okay, now Erasmus in 1509 gave a basic description of pre-Descartes thinking, which basically is where we are back again today. He said, there are innumerable niceties concerning notions, relations, instants, and formalities, which no one can pry into unless they have eyes that can penetrate the thickest darkness, and there can see things that have no existence whatsoever. The very state that Erasmus complains of in 1509 has been reborn in the concepts of relativity and what I refer to as quantum mysticism. Tesla states, the scientists from Franklin to Morse were clear thinkers and did not produce erroneous theories. Scientists today think deeply instead of clearly. One must be sane to think clearly, but one can think deeply and be quite insane. Today's scientists have substituted mathematics for experiments, and they wander through equation after equation and eventually build a structure which has no relation to reality. That's a pretty heavy statement for Tesla to make. Now, Edwin Armstrong, after being ripped off by RCA for his FM invention, really summed up the concept the best with the phrase, they substitute words for reality and then talk about the words. Heaviside gives his idea on what science is really about in his era, and very complicated statements. There is no self-contained theory possible apart from practical meaning. For a language is used in its enunciation, which implies that developed ideas and complicated processes of thought are already in existence besides the general experience associated therewith. We define things in a phrase using words. These words hail to be explained by other words, and so on forever in a complicated maze. There is no bottom to anything. We are all antipodeans and upside down. The misinterpretation of J.J. Thomson's discovery of the electron greatly hampered the understanding of electricity. And in 1900, Steinmetz summarizes the situation in one of his books. He says, unfortunately, to a large extent in dealing with the dielectric field, the prehistoric conception of the electrostatic charge on the conductor still exists, and thereby its use destroys the analogy between the two components of the electric field, the magnetic and the dielectric, and make the consideration of the dielectric field unnecessarily complicated. In actuality, it eliminates the dielectric field and makes it so that you can't calculate it and substitutes electron flow in its place. Wires are not conductors of electricity. This misconception of so-called conductors or wires carrying electricity like water in a pipe was continuously attacked by Heaviside in his writings. The entire article is written on the matter titled, A Perfect Conductor is a Perfect Obstructor, but does not absorb the electromagnetic energy of the waves. Heaviside states, it was discovered by mathematical reasoning that when an electric current is started in a wire, it begins entirely at its skin, in fact upon the outside of the skin, and that, in consequence, sufficiently rapidly impressed fluctuations of the current keep to the skin of the wire and do not sensibly penetrate its interior. The concept of electron flow in wires rather than electrical field flow around the wires can be related to seeing the footprints of the invisible man in the snow. Heaviside says now, very few, if any, mathematical electricians, he's writing this in about 1890, very few, if any, mathematical electricians could understand this fact. Many of them neither understand it or believe it. Even many who do believe it so do not because they are told so, I believe, simply because they can in the least feel positive about the truth of their own knowledge. An eminent practitioner remarked after prolonged skepticism, if Sir Thomson says so, who can doubt it? What a world of worldly wisdom lies in that remark. That's Heaviside's quote. The relativists, with their concept of distorted measurement or curved space, replacing an ether, and their concept of the equivalency of matter and energy worked great harm into electrical sciences. A post-Maxwellian theory of electromagnetism was to prevail, ignoring the works of Tesla and J.J. Thomson. Tesla states, "For more than 18 years I have been reading treatises, reports of scientific transactions, and articles on Hertz wave theory to keep myself informed, but they've always impressed me as works of fiction. Energy-matter equivalency, as propounded by the relativists, serves to distort the proper understanding of the continuity of energy as represented by Heaviside. The false doctrines of the law of conservation of energy has a deleterious impact on the findings of Steinmetz and others that electrical energy can be synthesized." Relativism sought to eliminate the concept of electricity in its entirety through the denial of the concept of the ether and plunged science into a giant glut of Platonic thinking and thereby established a type of religion called quantum mysticism. It seeks the creation of a spiritual entity such as a goddess in which to engender its framework of thinking. The influence, somewhat forceful, of the British thinking on science has been also a serious impediment upon the growth of electrical science. Foremost was the British Association, establishing a distorted system of units, ohms, farads, and what have you, representing electrical quantities. The effects were disastrous. Arbitrary factors such as 4 pi or the speed of light squared stuck to the electrical units like crap on shoes. The relativists took these parasitic factors, which have no meaning in real terms, and fabricated an entire way of thinking out of them. Heaviside used the phrase, "the brain-wasting perversity of the British." Euler describes British thinking on gravity as, "The English maintain that attraction is a property essential to all bodies, mutually to approach as if they were impelled by feeling. Other philosophers consider this opinion as absurd and contrary to the principles of rational philosophy." What was happening is the British were trying to say there was nothing in between the objects that attract, such as magnets, that it was purely the bodies themselves, and space in between was void of any acting material, which has to be complete nonsense if you're going to deal with electricity. That's where the ether comes in. English natural philosophers such as J.J. Thomson totally ignored the work of Americans such as Tesla. In fact, racial and national conflict played a major role in what would be established as scientific thinking. Nollet of France would rail upon the works of American Ben Franklin, the grandfather of modern electrical science. The French would enrage the English with their ideas on Newton, and hereby the English abandoned the ether concept for action at a distance in reprisal. Maxwell was to predominate over Helmholtz. The important works of Goethe and Steiner, who came up with a completely complementary concept of electricity and matter and these things that the British, through Newton, were working on, were completely ignored by the British and Newtonian thinking, even though the works of Steiner are extremely important in understanding certain electrical relationships. Racial mysticism such as Nazism or Zionism has given the world today a twisted nuclear thermodynamic science, producing a divergent culture racing towards destruction. Steinmetz regarded the Maxwellian concept of the transformer a fantasy. In fact, modern physics' representation of transformer action is the diametric opposite of that of reality. In the manner of Heaviside, let us tell a story. The story is entitled An Explosion at the Shipyard. The USS Lucifer, in need of repairs, arrives at the shipyard. It is on an important mission to deliver nuclear bombs to Israeli military forces in Iran. Dock electrician, a Mr. Young, came across a bag of meth and has not been seen in days. Substation transformer feeding the dock is not completely connected, and the USS Lucifer needs its power now. Lieutenant Junior Grade Einstein and Master Chief Electrician's mate, Heaviside, look at the transformer and find the pairs of secondary windings not completely connected. The work only partly completed by Mr. Young. Master Chief Heaviside, still sick from last night's liberty, heads for sickbay. He sends Seaman Lopez, who was recently demoted for fighting with blacks in the engine room, to assist Mr. Einstein. Seaman Lopez fancies himself as a real hotshot and is eager to jump in to assist Lieutenant Junior Grade Einstein. Mr. Einstein, having never seen a transformer, asks Seaman Lopez if he knows what the connections are. But Lopez replies he's never seen a split-winding transformer before. Now, Mr. Einstein, an MIT graduate in physics, remembers his Maxwell equations, which tell him, in his mind, that the induced EMF on the driven windings X1 and X2 must be out of phase with the induced EMF in the unconnected winding X3 and X4. Thusly, Mr. Einstein tells Lopez to connect X1 to X4 and X2 to X3. Lopez balks, feeling this may not be correct. Remembering back to electrician mate school, Mr. Einstein orders Lopez to make the connections or he'll be court-martialed for his fighting in the engine room. But Seaman Lopez is not stupid. Mr. Einstein exclaims the superiority of MIT education over naval EM school. The connections are made. Lopez closes the switch while praying to the Virgin Mary. Everybody's killed in the blast. That is where electrical engineering exists today. Sadly enough. Heaviside laments. The question is what now is to be done? Are we modern pygmies who, by looking over the shoulders of the giants, can see somewhat further than they did, to go on perpetuating their errors forever and ever, and even legalizing them? Upon the general acceptance of Einstein's relativity, Oliver Heaviside painted his fingernails pink, removed all the furniture from his house, and slept on a block of stone, and wrote no more. Okay, that's the completion of the first part. Are there any questions? Okay. So now we're going to get into basically what Steinmetz is about and this engineering mathematics that I'm going to present here. So Steinmetz came up with called the symbolic method of electrical representation, or what's known as the Steinmetz method. Engineering basically is built on mathematics and science, so we have to concentrate a little bit on what mathematics and science is about. Heaviside states that science begins with measurement of quantities. Mathematics is reasoning about quantities. Heaviside states electrical engineering deals with electrical energy and its flow, that is, electric power. Electrical engineers can be described as the goal-oriented utilization of the principles of mathematics and science. Theory must follow experience. Tesla complains that a spell cast by delusive theories has worked harm into the proper understanding of electricity. Heaviside advocates a somewhat forceful approach towards a correction of this type of problem, stepping on toes as one goes on, which is basically the air of this particular talk I'm giving. This might be the conversion from Heaviside to Michael Savage. To quote Heaviside, "This seems strong language, but as Professor Tate tells us, that it is almost criminal not to know several foreign languages, which is a venial offense in the opinions of others. It seems necessary to employ strong language when the criminality is more evident. It must be severe and logical." This is why Heaviside was eventually banned from writing, at least for a while. Upon giving up, Tesla states, "I am unwilling to afford to some small-minded and jealous individuals the satisfaction of having thwarted my efforts. These men are to me no more than microbes of a nasty disease. My project was retarded by nature and the world was not prepared for it. But the same laws will prevail in the end and make a triumphal success." I think you can see from the beginning of my talk that none of these people are very happy. Has anybody got that idea?
If you mix Mike Savage and physics, that kind of gets the idea.
What's that?
If you mix Mike Savage and physics, that does get the idea.
Okay, so now we're going to get into Maxwell, Heaviside, and Steinmetz, and how the electrical process was picked up by them. For 2,000 years, as Mr. Whittaker tells us in his book, the attractive power of amber had been regarded as a virtue peculiar to that particular substance, or possessed by at most one or two others. Amber being where you rub the material and it picks up the little pieces of paper, the original electrical experiences of the Greeks. Gilbert proved this view to be mistaken, showing that the same effects are induced by friction in a quite large class of bodies. A force which manifests in so many different kinds of matter seemed to need a name of its own, and accordingly, Gilbert gave to it the name electric, which it has ever retained. So the birth of the word electric then became established in 1646 AD. Michael Faraday, in 1831, makes public his theory of an electrified ether consisting of polarized corpuscles forming tubules of electric induction. He begins this study of the analogies between motional and statical electrical currents. Here begins the science of electricity. James Maxwell, in 1855, at the conclusion of Faraday's research and development of the contiguous ether concept, sets out to construct a mechanical model of electrodynamic actions. He wrote, "By careful study of the laws of elastic solids, the motions of viscous fluids, I hope to discover a method of forming a mechanical conception of this electronic state adapted to general reasoning." It has been said that Maxwell put the math to Faraday. The impact that Maxwell's ideas had on the emerging electric science was truly profound. Utilizing the recently developed ideas of Newton, Leibniz, and Hamilton, Maxwell produced a mathematical concept of electricity, one that stands to this day. Oliver Heaviside, in 1895, begins to publish a series of articles titled On Electromagnetic Induction and Its Propagation. Here Heaviside develops what he calls electromagnetic theory from the Faraday-Maxwell point of view. By 1888, Heaviside was banned from publishing through the efforts of a Mr. Preece of the British Post Office Telegraphy Administration. Heaviside was called a disgrace to the Royal Society. However, Oliver Heaviside established electrical engineering as we know it today. Heaviside finds that the Maxwellian ideas are so cumbersome and overly mathematical. A developed mathematician himself, Heaviside begins development beyond the concepts of Maxwell. Heaviside states, what is Maxwell's theory? Or what should we agree to understand by Maxwell's theory? The first approximation to the matter is to say, there is Maxwell's book as he wrote it. There is his text, and there are his equations. Together they make his theory. But when we come to examine it closely, we find that this answer is unsatisfactory. To begin with, it is sufficient to refer to papers by physicists written, say, during the 12 years following the first publication of Maxwell's treatise, to see there may be much difference between the opinions of them as to what the theory is. It's seen differently and by different men, which is a sign that it is not set forth in a perfectly clear manner and unmistakable form. There are so many obscurities and some inconsistencies. Speaking for myself, this is Heaviside speaking, it was only by changing its form of presentation that I was able to see it clearly, and so as to avoid the inconsistencies. Now, there is no finality in growing science. It is therefore impossible to adhere strictly to Maxwell's theory as he gave it to the world, if only on account of it being inconvenient in form. But it is clearly not admissible to make arbitrary changes in it and still call it his. He might have repudiated them utterly. But if we have good reason to believe that the theory, as stated in his treatise, does require modification to make it self-consistent, and to believe that he would have admitted the necessity of the change when pointed out to him, then I think the resulting modified theory may well be called Maxwell's. This is where Heaviside began his 1,500-page book called Electromagnetic Theory, which is basically the icon of electrical theory and science. Everything today basically rests on it. Heaviside published his 2-volume work called Electromagnetic Theory. It went to 3 volumes in 1892. Here he developed his reconfiguration and extension of the Faraday-Maxwell concept of electricity. Most terms used by electrical engineers, such as impedance, find their origin in these volumes. Oliver Heaviside developed a complete and verified theory of propagation of electric waves on telephone and telegraph lines. The brilliance right out of abject ignorance met with harsh opposition. But when AT&T developed the first long-distance lines on Heaviside's theory, the voices of the opposition were silent and their noses went high. By the Maxwellian concepts of Oliver Heaviside found institution in the telephone and telegraph industries, there were certain difficulties in the application of these concepts to the electric power transmission systems, particularly with regard to waves and transformers. By 1900, Charles Proteus Steinmetz had presented his theory of versor operators to replace the cumbersome differential equations utilized by the followers of Maxwell. Steinmetz was severely criticized, notably by Michael Pupin, who had glommed on to Heaviside's principles for AT&T, never mentioning Oliver, of course. However, Steinmetz's method was now a resounding hit amongst electrical engineers who now could forge ahead with Tesla's new system of alternate currents. This mathematical methodology thus allowed the extension of Tesla's AC technology throughout the world. Steinmetz quickly became an ultra icon of the United States of America. Heaviside began development of a similar line of thinking 30 years earlier with what he called his impedance operator. This concept, while replacing differential equations, was still too cumbersome for electrical engineers. In addition, it was Maxwellian. The Steinmetz method, being specialized for continuously alternating waves, was of such simplicity that one may get the feeling of cheating or such. In the corporate world that Steinmetz worked his concepts of versor algebra in, as it is called, let's see, I think I skipped something here. He could never advance it as far as he might take it. The companies were not interested in math, they were interested in machines. While attending a paper presented by Michael Pupin on the Tesla induction motor, Steinmetz remarked that the differential equations made it too mathematical for practicing engineers. He quickly sketched on the blackboard his complex number theory, which was simpler mathematically and also accounted for the losses. Not possible in Maxwellian terminology. Upon finishing, Steinmetz was criticized for not using Maxwell coefficients by Pupin. Steinmetz disliked the Maxwell approach because the coefficients of mutual inductance were expressed in a combined form as one magnetic field, where in actuality, in transformers, they exist in two fields, in what Steinmetz calls the mutual flux and the leakage flux. This conception is of utmost importance and serves as one of the main themes of this paper. So Steinmetz was given credit for being allowed by his employer to create electricity from the square root of -1. And this is where we enter the basic theory of the talk. Is it possible to synthesize electrical energy? So, a Vladimir Karapetov, professor of electrical engineering at Cornell University, expressed that Steinmetz was allowed by his employer to create electricity from the square root of -1 at the eulogy of his death in 1923. This appeared in the Cornell Daily Sun on the 29th of October, 1923. Before the Steinmetz method, engineers had used differential equations or graphics to calculate alternating current problems. With all the mathematical baggage aside, engineers could see the alternating electric wave with crystal clarity. In this view, a few engineers knew that electrical energy can be synthesized, literally created along certain lines of mathematical reasoning. At a lecture of the American Institute of Electrical Engineers, in which Steinmetz, Tesla, and others threw their ideas back and forth about these, Professor William Anthony stated at the closing of the meeting that within 1 year they were going to have a self-sustaining electrical system that didn't need any fuel. This was in the 1890s. Where is it today? Steinmetz began study of what's called synchronous parameter variation. The meaning of this is the variation of energy storage coefficients, such as inductance or capacitance or resistance, with respect to a point in time on the AC cycle, is the cause of what Steinmetz says, is caused by what Steinmetz says, the lack of uniformity and pulsation of the magnetic field, causing a distortion of the induced EMF at open circuit as well as under load. The pulsation of reactance causing higher harmonics under load. He's speaking about generators and motors now. The pulsation of resistance causing the same harmonics. That was the big flame you saw at the beginning, leaping off the disconnect switch. Now the normally constant or time invariant coefficients change in value with respect to time. Now we have a peculiar set of dimensions of Henrys per seconds, ohms per seconds, farads per seconds, and Siemens per seconds. And this is where the concept of the law of conservation of energy comes apart. Because the energy is appearing and disappearing in these relationships without any equality or connection anymore. Energy can either vanish or energy can appear in the system. Steinmetz states in Article 241 of his Theory and Calculation of Alternating Current Phenomena, published in New York in 1900, the following. We find here a case of a circuit in which the power factor, that is, the ratio of watts to volts amperes, differs from unity without any phase displacement in the phase of the cycle. That is, while the current and the EMF are in phase with each other, but are distorted, the alternating wave cannot be replaced with an equivalent sine wave, since the assumption of equivalent sine wave would introduce a phase displacement of an angle that doesn't exist. This condition made itself apparent in the line switching equipment of the primordial electrical industry. Let's see if we have some of these. Now this is a prime example of what happens. Okay, we're trying to turn off a 220,000 volt power line, and this is the switch. It stands about 50 feet high. Now what they've done is, in order to eliminate the oil tanks, which normally break the main discharge, they're using vacuum columns. And what it is the mechanism breaks the circuit inside the vacuum columns. But being that there's no gas or oil or anything to carry the current through to the zero part of the cycle, the voltage tends to,
That's your laser.
the voltage tends to raise to infinity, trying to maintain the power flow. This is where the switches start to explode as they're opening here. Now normally these cells here break the electrical circuit in the vacuum so there can be no arc, but that's kind of the last thing you want to do, because the momentum of the electricity will come thundering back down the line to try to keep it going. And what I just read from Steinmetz is in the actual arcs where the switch contacts are breaking open, is you start to get energy anomalies in these arcs. And the system goes into a cumulative oscillation and continues to accumulate energy until something blasts. So as we go through the opening of the switch, you can see where now the fire has jumped across and there's no way to stop the flow and it's just accumulating. I think we've got one more shot before it explodes. There we go. Now it's getting ready for the final blast, and then the final shot, that's another switch. Okay. That's the final shot where it shorts out the power line. The intensity of the light's so great that the camera can't really, it's shorted out the camera. So you can't really see you can't see it at this point very clearly. It fuzzed it out, but that's a lot of power there. You're talking about the electrical discharge there is probably equivalent to maybe 20 locomotives running full bore, hauling trains over the Tehachapi Pass.
But I'm sorry, I just want to get this right, because it's interesting. A plasma is established inside these vacuum switch chambers?
No, the whole idea is to have no plasma.
Right.
But being that the current is not cut off at a zero point in the cycle, as the electrical momentum starts to come thundering back down the line to maintain the current.
So a plasma is created in this process?
No, inside it does not create a plasma, but the problem is the voltage gradient goes so high. Can we go back to the first one?
Sure.
When it first starts to blow. Okay. What happens is it's the voltage gradient now, the electric field around this. We'll get into it later. This is not just objects in isolated space.
That's
right.
fine.
The electric field density has become so severe, okay, that it has to strike out in the atmosphere to create a plasma because it can't create it in the switch. So you might have an electrical field here in the order of maybe 10 or 15 volts per megavolts per centimeter. And so the fire breaks out. See, normally when the switch opens, the remaining fire is dissipated in these opening arms. As you see going through the video, it goes step by step. These were live pictures, but we couldn't have they're stunning to watch move. So you can see now the arcs have come off the switch and now found their way back to the line terminals. And there's no way to stop this now. And then the arcs are changing resistance. This is the key thing. The arcs are cyclically changing their resistance with respect to time on the alternating current cycle. And in the process of doing this, they're creating a imaginary, or I wouldn't say imaginary, but another dimensional energy that has to come out into this dimension. And this is a process very worthy of study. This is what Steinmetz is mentioning here in Article 241.
Then I would like to, one thought, because a lot of folks keep getting, like Art Bell for instance, keep getting these mysterious voltages occurring on their antenna arrays, is that related to this concept here?
No, not directly.
But it does indicate that there's something else coming in from a different dimension set maybe.
Well, what it is, it's basically mutual induction to the ionosphere and the sun. And those electric fields are always changing, but it is an electrical gradient. But there's no plasma other than the sun itself. But then we're getting into a system with much larger dynamics and more factors come in.
So that makes sense.
Right. Okay, so let's see. Okay, the condition made itself apparent in the line switching equipment of the primordial electric industry. Large transmission lines and substation transformers refused to be de-energized without some large fire or blast. This is a substation going up when they couldn't turn it off. So three shots here. So this is what they were dealing with, and it wasn't a happy situation, and they had no way to stop it. If you tried to turn the stuff off, this is what would happen. And people got unfriendly about it. Not alone the people that paid for it. The condition, it was not as if they were creating their own energy. Let's see, I left off something here. AC power distribution could not progress because of this condition. It was as if they were creating their own energy, and this energy would not appear on the switchboard instruments of the power system. Energy now had a new meaning, and engineers felt a new era in the process of making. This is when Steinmetz wrote his next famous book, was on this topic. Situation came to a head to a crisis level for both GE and Westinghouse, who were pointing the fingers at each other that their line switching equipment was, the other guys was bad and theirs was good. And they couldn't share the deal, so when the whole thing blew up, they had to start pointing the fingers. So what happened is the electrical system for the Manhattan Elevated Railway is what we're talking about. So the Manhattan Elevated Railway blast and ensuing shutdown in 1903. At the time, it was the world's largest steam-driven electrical generating plant. The capacity was 40 megawatts with a voltage of 11,000 volts from phase to phase. Singing static discharges of surge arresters began at one railway substation, and then at another railway substation. Shortly afterwards, a massive underground blast raised the street around the splicing manhole. Many of the 5 megawatt alternators suffered damage. Upon analysis by Steinmetz, it was that a progressive or cumulative oscillation had developed, evading station voltmeters. This oscillation cohered at 270 cycles a second in the entire electrical system with a wave crest of 120,000 volts. That's a lot of buildup over 11,000 volts. And the final fault current was a fault current of 9,000 amperes. So we're talking about a pretty good bang. That's why the whole street lifted up 2 or 3 feet. Out of this work, Steinmetz developed the synchronous condenser, a type of dynamotor that one may be tempted to call a free energy device. This machine is utilized by the utility companies to provide part of the power to their transmission system that would otherwise have to be produced at the distant generating facility and thereby cause a waste of power in its transmission. So basically, the electrical power industry is in a certain sense already using so-called free energy concepts because it's inherent in the distribution system itself when it gets to a certain size. And we're using the synchronous condenser, which is a very large synchronous motor that's immersed in hydrogen gas. The reason it's immersed in hydrogen gas is to cut the windage down, and hydrogen is a heavy absorber of heat. So they can keep the machines cool and they can keep the windage losses down. The motor only connects to itself electrically. And through this synchronous parameter variation, what this motor does is become a generator by working its own phases inside and supplies all the magnetizing power for the system necessary to keep the transformers and transmission lines magnetized. And between the synchronous condenser and the substation at the distance end, through my experiments, I've determined that energy is actually synthesized in the space between the wires in the magnetic field. Now, I did an experiment with this when I was at the Richmond shipyard. So these are our basic lines of force that we're talking about. They don't show up too clearly on this screen. There we go. So if we have an electrified wire, the wire is not carrying the electricity, but it's this induction in the space surrounding the wire that represents the electricity. The radial lines are what are called the electrostatic, or as Faraday called them, the dielectric lines of force. The circumferential lines are the magnetic lines of force. And in every point in space, they exist at right angles to each other. So one is basically the antitheses or the denial of the other. This will be the repeating theme that we will see through this whole lecture, is the conjugate relationship between magnetism and dielectricity. Now, at every point at which these lines cross,
where the radial lines cross the circumferential lines, this represents electromagnetic energy, and it is flowing into or out of the paper parallel to the axis of the wire. At that particular crossing point, we call that the unit of the Planck. And in Einstein or quantum ideas, it's called a photon. We go to the next one. Okay, now when we have a system of conductors which bounds the electric field, then it becomes trapped by the wires. That's why there's always more than one wire used in transmission systems, is to bound the ether between the wires. So now we have the radial lines of force are tending to pull the wires towards each other mechanically by shortening. The magnetic lines of force, the circumferential lines of force, are tending to fill the space between the wires and push them apart mechanically. At a certain stress point of the dielectric, which we would call the voltage, and a certain stress point of the magnetic, which we would call the amperage, the two forces counterbalance each other and no force appears on the wire whatsoever, and this is called the natural impedance of the system, where the two energies are balanced out. We're going to get much deeper into this electric field. So if we're looking down the power lines, then this is the two wires, and we'll get deeper into this later as we go down. Let's go to the next one. Okay, so here's iron filings around the magnet, and you can see them lining up with the lines of force. In fact, actually, I have magnets passed around. Does somebody have those? The idea is, are they passed around? I thought I heard somebody clicking them. Is that you, Bob? You got the magnets? Well, if we don't have them, well, I wanted you to actually feel this, but we didn't have time to put together a good model. Okay, let me go on here now. Okay, so we haven't got the Maxwell cells. Let's keep going. Keep going. We can always go back. These are various lines. Here we go. This is Maxwell's paper on the ether and lines of force. Let's keep going. Okay, now this is a drawing out of his notebook. So this is what Maxwell thinks that the ether structures into in its electrified form is this cellular construction. And then afterwards we can read it. He gives us description. Go after it, then we'll read what he says. I suppose that the magnetic medium is divided into small portions or cells. The division or cell walls being composed a single stratum of spherical particles, these particles being electricity. The substance of the cells I suppose to be highly elastic, both with respect to compression and distortion, and I suppose the connection between the cells and the particles in the cell walls to be such there is a perfect rolling without slipping between them, and that they act upon each other tangentially. I then find that if the cells are set in rotation, the medium exerts a stress equivalent to a hydrostatic pressure combined with a longitudinal tension along the line's axis of rotation. If there be two similar systems, the first system, a system of magnets, electric currents, and bodies capable of magnetic induction, and the second composed of cells and cell walls, the density of the cells everywhere proportional to the capacity for magnetic induction at the corresponding point of the other, and the magnitude and direction of the cells proportional to magnetic force. Then, I think we have another page. So he makes his propositions here. We won't go through all this because it's a little more complicated. So let's go back to... let me do some more reading here and go back to the first flux diagrams. Okay, further back.
Don't be afraid to use your laser pointer.
Okay. Yeah, let me, that might be helpful. Okay, so here we have the crossing points. Okay, that's the electromagnetism. Then we have the circumferential lines of force, which is the magnetism, which is rotary in character, and is basically dimensionally considered velocity. Now we have the dielectric lines of force, which are everywhere at right angles by definition, being the antitheses of the magnetic. So basically, one becomes the gradient lines for the other. One defines the other in a conjugate or mirror sense. Now these lines of force move along in this direction. Now the magnetic lines of force must surround in closed loops the electrical or electrified objects. They can never end in space. In other words, this is just because it's gone off the paper. The dielectric lines of force must always terminate into what we will call counter space, or what J.J. Thomson called intermolecular dimensions. So by more conventional theory, we can say that this line of force is stuck to an electron on this wire, And this line of force is stuck to a proton in that wire. That would be your more physiochemical representation, but no one really knows what's going on inside these wires. And the electricity all moves this way down the paper at the speed of light. The ratio of these two quantities must always equal the speed of light. This was Maxwell's fantastic discovery that not only is the speed of light a velocity, but it is also the constant ratio between the amount of electrostatic or dielectric and magnetic energies in the system. And the impedance of this type of configuration always tends to be, again, a numerical value based on the geometry. But the speed of light has this duality, and this is where the confusions of Einstein and relativity and everybody emerged from, was this duality of the electric field as discovered by Maxwell. So I'm going to read some more Maxwell. We've gone through his cells. Okay, J.J. Thomson, as well as Heaviside, altered the Faraday-Maxwell concept such that now an electrostatic field constituted the tubes of force, and that a magnetic field was a secondary effect, what Faraday referred to as the dielectric field. J.J. Thomson used the term Faraday tube to describe a unit line of electric force. Let's go to J.J. Thomson's diagrams. Okay, here, the back. He's showing the attractive force exerted by dielectric lines of force between two bodies. Now, Thomson felt, unlike Faraday felt that the lines were magnetic, but Heaviside and Thomson felt that the dielectric were the primary and the magnetism was just that circling around the dielectric. You know, it's kind of like a chicken or egg consideration that's never really been fully resolved because the ether has no tangible physical dimensions. Okay, now what's happening is these lines of force tending to be contractive pull the plus and minus together. And this basically is a representation of the process of attraction. Now we go to the next one, we have the process of repulsion. So in the process of repulsion, we don't have lines of force pushing the two objects apart. What it is the lines of force now have to terminate on more remote surfaces of molecular dimensions. And what it does is it pulls them away rather than pushes them away. So the repulsive process is not really a pushing apart, it's a pulling apart. And there's a void here in the middle of the absence of electrification rather than a concentration of it. Okay, now Euler's ether, and one which was prescribed to by Tesla to compensate for, or to give an idea of gravity, that's further down the line here. We'll just cover that one briefly because it's specialized. Okay, now both Euler and Tesla felt that there was a type of gas where the mean free path of the particles was so intense because of their extremely high velocity that they would never hit each other in any fathomable distance through space. In other words, they could go for light years through space without hitting each other. It's a peculiar type of gas. Tesla confirmed the existence of these particles, which he called his cosmic rays, which are not really connected to the cosmic rays as they're told today. He had discovered a primary type of cosmic ray, which he said moved at 50 times the velocity of light. Now, what these guys all thought is that what gravity is, because it's not just simply two things attracting, something has to make them pull together. And we saw by the lines of force that what appears to be pushing apart is really pulling apart. Then if we look at it this way, is if these randomly moving ultra-gas particles strike an object, many of them will go right through. But these rays can be detected in the deepest mines of the world without suffering any attenuation. They can go right through the planet, but a certain amount of them will hit something. Now what happens is that creates a dead zone. So now you no longer have a uniform pressure of impacts around the object because the mean free path is so extreme that what it does is now this void zone, you have more lines pushing here and more lines pushing here than you do here or here. And this is what causes objects in space to move towards each other, is they're actually pushed externally. It really is the most sensible view of how gravity operates. But it leads to some conclusions that are very unpopular. Because by this type of theory, all of the planets and the sun have to be hollow. And people don't like to talk about that. So Tesla also regards the ether as a gas. and succeeds to produce these ultrafine high-speed particles in his vacuum tubes. Now, I've duplicated this in an experiment. He claims velocities 50 times that of light. Tesla's tubes gave the ether the properties of mechanical force against ponderable matter. I'll describe an experiment I did where I took these special Tesla type of currents that we'll get into later why they're different and energized light bulbs with them. Well, the light bulbs don't light up like normal on this because this is not normal electricity. So this kind of solar system or galaxy starts to appear inside the bulb with little suns and comets and stars and gradually becomes cumulative like these power line oscillations. And what happens in this process is that actually, even though that the bulb has a vacuum or partial vacuum in it, is the glass when heated starts to push out. Something is pushing the glass out. So what has been done is the ether now has been solidified into something that can exhibit physical force against matter. Now when, has you got a screw up there? I'll wait till the screw up's over.
I'm sorry, what?
Oh, the one with the lights blinking and you guys are talking, so.
Next slide?
Did something, no, I just thought you had a problem.
Yeah, well, just with the videotape.
Okay.
We're still rolling over here.
Okay, so what happens is this entity inside the bulb produces so much impact and heat on the glass that when it melts, it'll melt a hole in the bulb. Now, you would think when a hole is melted in the bulb that the air would rush in and wreck the partial vacuum and the bulb would cease to work. Well, it's the exact opposite. What happens is this purple ether comes shooting out of the hole like a little air compressed jet and hisses, and the vacuum in the bulb becomes stronger. So this completely turns the concepts of what's inside empty light bulbs inside out. Steinmetz regarded the existence of the ether as a reality, but changed horses when the concept of the ether was eliminated by the Einstein concept of distorted measurement of what is called relativity. A natural philosopher by the name of Lamore, at this point, says we should not be tempted towards a simple group of relations, such as Maxwell had tried to create, which have been found to define the activity of the ether by treating them as mechanical of concealed structure in that medium. We should rather rest satisfied with having attained their exact dynamical relations and not be into describing a physical, because they're not physical. Okay. Now, it looks like I've run out of material here for some reason. There we go, on the sheet. Okay, so I think we need to start going through these. It was very difficult to get all this together in time, and most of it got like lost or shuffled, or this talk came hot out of the oven. So let's go through here, and then I'll start talking about. Okay, well now we're going to get into a more practical situation. So here we have a long-distance telephone line, a basic, simple reality, and we're going to focus in on that. So we're going to look a little closer. I'm doing measurements on it with my car. You can't see the antennas. I think you can kind of see them up in the front. They're about 10 feet high. The car has equipment in it to give it the ability to sense the way insects do with their antennas through the electrostatic field. That special equipment inside the car right now determining what kind of forces are around various power lines and rocks and those type of things. It's part of my research. Okay, we'll take another shot. Okay, now we're into each individual transmission pair. Okay, we'll focus in tighter. So this is what we're dealing with. Okay, now we're going to go to a graphical. This is what we have. There's the two wires. Okay, and we have an impulse started at the sending end, going to the receiving end of the wires, and then the diagrams are the conversions of the ether in the space between the wires into what are called electrical constants of inductance and capacitance and resistance and conductance. And then the field diagram between those two wires, which we go back to the two wires, then we go back to the field diagram. Field diagram. No, back to the field, other way, back to the field diagram. Okay, now those are the two wires cut sideways, and these are the two wires going end to end. So let's go to the next slide. Okay, now we're going to start to take this space apart between the wires. So we're going to start with the quantity of total electrification, which we're going to call the Planck. Okay, and this quantity is going to be considered undivided. That's the basic electricity between the wires. Okay, and this consists of two parts. One is called the total magnetization in Weber's, and that's the Greek letter phi, and the Greek letter psi is the total dielectrification between the wires in Coulomb. So let's go back to the space between the wires so we can show where these things exist.
There you go.
It's playing games with me like all this technology does. I guess I have to hold it. Okay. So this here in this diagram is the dielectrification. And we're symbolizing the totality of the dielectrification, in other words, the total number of lines of force in our system, which is the span between two utility poles, okay, with the Greek letter psi. The magnetic forces, which form the circumferential circles, we're taking the total quantity of that between the two poles, and we're going to call that the Greek letter phi. And then the point at which these unite, the net sum of all those, we're going to call Q, or the total electrification of the system. So let's go back to our equations. So we have the total electrification, and then we have the magnetization and the dielectrification, and these are named after Planck, Weber, and Coulomb. So let's look at them. There's Max Planck. These are all very famous people. A lot of them you don't even hear about. Let's go to Weber. These are the guys that basically created our technology of today. And then Coulomb. Okay, let's go to the next. Now we're going to start to get this stuff broken down. So we get our basic relationships. So if we take the ratio of the total electrification to the total dielectrification, then that gives us the magnetism in Weber's. If we take the total electrification, the ratio of that, to the total magnetization, then obviously that gives us the total dielectrification. And the electrification is the unqualified product of magnetism and dielectricity. In other words, these are the two aspects of dielectricity. This is the outer space aspect of dielectricity, and this is the inner space aspect of dielectricity. Okay, let's go on.
That X there, that's the cross product, not
That means multiplication,
not the cross product.
but not generalized, not qualified multiplication. It can be any type of product.
If I were to take a macro view of this, would I be looking from this interpretation as...
Can you speak up just a little
Sorry,
louder?
if I were to take a macro view of this concept, because that's kind of how I see this, I'd be looking at density patterns in the ether. Is that kind of what you're interpreting?
Exactly.
Okay, so then you have like flux patterns.
Right.
There's a waveform actually fluctuating through this ether.
Exactly. Yeah, that's where I'm developing these ideas now.
I
So.
don't get the point.
Right. Okay, now normally somebody mentioned cross products, so let's go back. Let's go back to the...
Excuse me, that's centimeters to the fourth there? I just want to make sure I understand that.
Uh,
Go back to where you were a second ago.
but we're not using that yet.
Bottom on the right.
I know, but we haven't got there yet. Let's keep going back. We have to retrace our steps because people have asking questions, now I have to define. Okay, go back to the diagram. All the way back to the diagram. Okay. Now this is what's called an electromagnetic configuration, but not, as we'll see later, not all configurations are electromagnetic. Now in this case, this is the cross product. But as we'll find later, the multiplication is more general than that. That's basically the whole crux of this talk, is to come up with the non-electromagnetic, or what we would call the Tesla component. So let's keep going then. Okay, now... Okay, so this is we're basically just saying here that magnetism and dielectricity are the two components of electricity. Steinmetz eliminated the use of the word electric field because it's not correct. He called it the dielectric field in Faraday's terminology. Everybody has agreed upon the magnetic. In Steinmetz's electrical theory, electricity has to be the product of these two quantities. If it's just one or the other, it's not electricity. So a charged capacitor is not electricity. Okay, a trapped magnetic field in a motor winding is not electricity. It's only when these two things cooperate interdimensionally with a relationship where the energy of one is exchanged into the energy of the other through a cyclic process do we have the appearance of electricity. Okay, let's go on. Okay, so now when we start to deal with this stuff in space, we start to get into some complexities, and that's what I'm trying to present here. So if we take the total magnetic densities Okay, and on a per area basis, in other words, we have lines per square centimeter. We call this, let's call this the density of magnetic induction, which would be in Webers per centimeter squared, in other words, square centimeters. Okay, obviously we can do the same thing for the dielectric condition. So if we have a cube sitting in there, in between the wires, there's going to be a certain number of lines of force going through this 1 square centimeter clear plastic cube that the waves just go right through. The wires are just the boundary. The electricity is flowing in this dielectric between the wires. This was Maxwell's profound discovery, that electricity does not flow in conductors. In fact, actually, in the days of Franklin, metals were called non-electrics because they destroyed the electric field. The complete opposite conception of what's been put in our minds today. Okay, we have an interesting situation. Now, if we try to take this back to the electrification, we have area squared, and this is going to pop up again and again, is now we have the dimensions of space to the 4th power, which a physicist would be tempted to call 4-dimensional space, but we're going to modify that concept because that leads errors into the mind state. So we're going to work around that, and I'll get into that a little later. So basically, these are just our basic tenets of what's to follow. What I'm trying to do is so that everybody knows what these terms that we bandy about are, like volts, amps, ohms, watts, coulombs. Everybody uses these words in electricity, but nobody really knows what their definition is. I could ask everybody in this room what a volt is, and I would get a different answer, and chances are almost everyone would be wrong. But we're going to learn what a volt is. So let's move on. Okay, so if we take the quantity of electrification and we vary that with respect to time, in other words, it gets stronger or weaker or moves somehow so that in time its quantity changes, we call that work or energy in joules. So in other words, energy does not have a primary existence in this electrical theory. Energy is actually a derivative. So we have all of our derivatives of electric fields here. So if we have the magnetism, the total magnetization, and we vary that with respect to time by strengthening or weakening the magnetic field, that gives us E, electromotive force in volts. So that when someone asks you what a volt is the rate at which magnetism is produced or consumed in an electrical system. That is the definition of a volt. Okay, now if we take the total quantity of dielectrification, okay, and vary that with respect to time, in other words, we either produce or consume a dielectric field, and it changes with respect to time, we call that I, and that's called the magnemotive force in amperes. Okay, now if we take the quantity of electricity and vary it to the time squared, or if we take the product of these two, which gives us this. In other words, this times this gives us this. We call that power P, or activity. P is the power activity in watts. So then we'll look at the people whose names we're using. So there's Joule, Volta, Ampere, and Watt. These were the people that conceived these ideas that we're talking about now. Okay, we'll go on to the next. Okay, now what we're going to do is we're going to get into the proportionality of the situation. So if we have a magnetic field and we have a current which is associated with it, we take the proportionality between the two, that gives us L, or what we call the magnetic inductance. And that's given in henries. So the inductance of an electrical system is the magnetism compared to how much current is required to produce it. So if I can produce 100 units of magnetism for 1 unit of current compared to 1 unit of magnetism for 1 unit of current, the 100 units of magnetism for 1 unit of current would have 100 times the inductance of the other situation. So it's a basic proportionality. Now the same thing exists with the dielectric field. If there's a dielectric field and there's a voltage, or in this case a potential associated with it, then for every quantity of dielectric field there has to be a certain amount of electromotive force that gives rise to that dielectric field, and we call this proportionality C, or the dielectric capacity, in farads. So we have henries and farads. This is called inductance, and this is called capacitance. These are all things I think a lot of people have heard about, but never really got a definition of what they meant. These are basically geometric proportions determined by the configuration of the so-called conductors and insulators, and do not change with the actual quantity involved. It's merely the proportionalities of the quantities and their inner workings. Now, if we take the ratio of the electromotive force to the magnemotive force or current, we call that Z, or impedance, and this is given in ohms. And conversely, if we look at it from the dielectric point of view, if we take the magnemotive force or current and take the proportionality of that to the amount of voltage or EMF or potential in the system, that gives us Y, which is called the admittance. This was a word developed by Steinmetz. This was a word developed by Heaviside to describe these things. And that's given in what are called Siemens. Then we'll look at the people that are attributed to the development of this. Henry was an American, by the way. He was called the American Faraday. But he being an American, the British made sure that he was kind of left out of the story, so you don't hear about his experiments. But without him, Morse couldn't have developed the telegraph, because Morse was a painter and an artist. He was not an electrical engineer, and he needed Henry to wind all of his coils. Okay, then we have Faraday. Faraday is basically the granddaddy of all of this. They call him the Columbus of electricity. It was his experiments that started the electrical age. He used no mathematics. It was all done with pieces of wood and bottles and things like that. No big giant Livermore labs, none of these things. Yet his work stands to this day. Okay, we'll go on. Then Ohm, he was the one that found the proportions between these constants that we saw earlier, like the amount of electricity to the amount of magnetism, or the amount of volts to amps. They didn't have a lot of these words back then. Made it hard for them to work on. There was no volt or amp or ohm. But Ohm was the one that worked these relationships and produced them for the first time. Then we go to Siemens. Siemens was successfully created one of the world's first long-distance telegraph lines that went all the way from Russia to India. And massive quantities of scientific information were gleaned out of this, and this is basically what started Oliver Heaviside, because he was the first mathematician to analyze the telegraph and telephone line, which created our modern engineering mathematics. Okay, let's keep going. Okay, now we have a situation that's a little different, and these are where our energy anomalies occur, is in these type of conditions. Okay, if we have the inductance of a system, and we vary that with respect to time, in other words, if I have an electromagnet and the core is moving, so that like in a motor, so that the inductance is varying with respect to time, we call that R, or resistance, okay, which can be either given in henries per second, but customarily we call that an ohm because it's in the same dimensions as impedance. And then conversely, if we vary the capacitance with respect to time, we call that G, or conductance, which in America they use Ohm's name backwards, or Mo, which is inconvenient, so I stuck with the Siemens because that letter S is actually needed later down the line. So it turns out to be in a generalized electrical system, this component represents the destruction of energy, and this component represents the creation of energy in an electrical system. Whether it either be synthesized, or it converts from electricity to mechanical, or it converts from mechanical to electricity, then these are the ways that it goes back and forth. So your light bulbs, your space heaters, your motors, your computers, all that type of stuff involve these relationships so that the electricity can find its way out of the system and appear as heat or light, or in some cases be dimensionally dematerialized and disappear completely from the system, which does happen. Okay, and then if we take the product of these two terms, it gives us the dimensions of time squared. So if we take the square root of the inductance times the capacitance, that is how we derive what's called the frequency of oscillation. In other words, there has to be a time rate of energy exchange between the magnetic and dielectric field as they constantly dump from one into the other. We're going to get into the mechanism of that a little further down the line here. Okay, we'll go to the next. Okay, this was actually for a dimensional situation. We couldn't get that in the right spot, so we'll have to go back to it.
Well, why are you doing that?
What's that?
Why are you doing that?
Because
it seems to me that what you're proposing is sort of like, in a sense, an antenna that can capture these fluctuations in the ether. as a way of harvesting this other energy. Is that one way of looking at that?
That might be like an extrapolation of it. But basically what I have determined in my research and with this mathematics and experiments and other people's work is that energy can be taken apart or put back together.
No argument there. So if you have this potential for somehow capturing these fluctuation or density patterns in the ether, that in itself might be instigating what looks like apparent electricity.
Right. Well, if you take a situation, okay, we're standing right now in what appears to be motionless space, right? Nothing's moving except for our basic, milling about. But the thing is the Earth revolves on its axis. So we're moving in a certain direction at 1,000 miles per hour. But then the Earth goes around the sun. Okay? So if the Earth is going around the sun, now we're up to about 60,000 miles an hour. That's how fast we're moving through space right now. Now if we take how fast is the sun moving through the galaxies, okay, these numbers just keep on building up. Now let's say we view this as a railroad train. Okay, now if I'm on this railroad train going 250,000 miles per hour, okay, and I take this thing and I throw it off the train, what's it going to do? It's going to make a big blast, right, when it hits the ground? If this thing is moving at 250,000 miles through space and it stops against the wall, there's no gun that shoots that fast. That is how much energy we have right now in our bodies flying through space.
But when Einstein talked about frame drag, he actually talked about the elasticity of a time-space continuum being manipulated or stretched by a revolving body or by other forms of mass. So in a way, you're kind of looking at that idea a little bit.
Well, I'm coming about it from a way where it's actually on physical dimensions and not with the metrical dimensions. I'm going to get into that later. That's what those other diagrams... Let's go back to those diagrams. Okay, I was going to do a little coverage on dimensions here because this is part of where the mind virus appears and it really has to be corrected. So let me try to read from this. The computer hated this whole talk and just fought it the whole way. So I have determined, I don't normally use that technology because it's repulsive to me, but I have determined what is the creators of this technology are doing, are introducing what we call nemesis into the systems, okay? And the way I look at it, the people that create this technology are a bunch of geeks. And what it is they're creating their geekdom in the machine, and the geekdom feeds on your tension or what you're doing that doesn't fit into what these people like to hear. A friend of mine referred to it as a Trojan horse. I won't say any more about it because that's exactly what it is. So everything you pretty much see here, I have been involved in this about 20 years, but just about all this I put together on park benches as a homeless person here in San Francisco for 10 years. I didn't need any computers. It's quicker not to use the computer. You use paste, you use paper and scissors and a photocopy machine. So let's go back to this. Okay, so we're going to deal with the concept of dimensions because this is something that needs to be cleared up before we go back to the ether. Okay, the definition of dimension. One of a group of properties whose number is necessary and sufficient to determine uniquely each element of a system of entities. That's kind of a choke of a definition. Now, the misuse of the word dimensions is where it's not the case. We're not using dimensions in this term. Okay? Dimensions are not to be defined or expressed as a directional measurement or a number of coordinates, such as a three-dimensional space. There's only one dimension to space. Hereby, space is a solitary dimension, that there exists only the dimension of space. Expressions like four-dimensional space-time or two-dimensional space have no meaning. Space-time, then, is simply the relation of two distinct dimensions, the single dimension of space and the single dimension of time. As an example, velocity is expressed as the ratio of the dimension of space to the dimension of time. That is, how many miles of space for over how many hours of time. Miles per hour. Thus, velocity is expressed as a two-dimensional relationship. Okay, now if we take the dimensions of time, okay, we have two expressions of time in electricity. We're not confined to our normal so-called rational ideas of what space or time is. Space or time are basically measurement processes. They're not physical processes. So time can either move in a forward direction or it can move in a backwards direction. And in an electrical system, any generalized electric wave consists of a superposition of a wave going forwards in time and a wave going backwards in time. And the point in time which they cross is the crest of the wave. Okay? In the dimension of time, we move in an additive or a subtractive manner. In other words, our operator is +1 or -1, and time is multiplied by this operator. So time is either plus or minus. Space is entirely different, and this is where the problems start to appear in electrical research. Okay? Space, in this case the letter L for length, is now the operator exists in the exponent. So we have outer space, or we have inner space. So it's plus and minus in either it's in an outside space, like the space of real estate in acres, or it could be an inner space, such as in between the molecules and electrons inside a transistor. So inside the transistor, we have a condition of inner space, or what Rudolf Steiner called counter space. That's the term that I use for this. It's called counter space. There's space and counter space. But in order to make it truly a duality, we call one outer space, which would be the space outside the wires, and then we have the inner space, which would be the space inside the wires. And we have the exact same condition in the ether. Okay, and if I take space, I can take space such as I can represent that blackboard by a certain number of square centimeters, and that is in the dimensions of outer or space. But if I take a ruler and I look at the space in between the lines, I call that inner space or counter space. So space is measured in centimeters. In this case, in other words, it's to the positive exponent. But counter space is measured in per centimeters. In other words, to the negative exponent. So this is a very important consideration. Now we go to the next one. There's two systems of logarithms that are in general use. The upper system of logarithms, which gives us our normal trigonometric functions of sines and cosines, and also can give us our hyperbolic sines and hyperbolic cosines. And it's based on a Newtonian mathematical operation where you go through this process, and that is the way you express your so-called trigonometric relationships. It makes the equations work. In other words, I can have 2 pi radians, and that tells me that that's one circle, but it has to be in this basic mathematical form. But there's another one that's called the golden ratio. Now what's interesting about the golden ratio, that is this particular expression. Now in the golden ratio, we find that if we have the golden ratio, which would say the letter A, just to represent that specific ratio as a quantity A, if I subtract it from 1, I get the same answer as if I take that A and I raise it to the -1 power. So if we go back, the golden ratio, ultimately, this is one of my projects I'm working on now that I have no more equipment, I only can get involved in mathematics, is to come up with a system of logarithms that utilizes the golden ratio to attempt to bring these two dimensional representations together. Now what Steinmetz did in his study of power lines is, in order to eliminate having to use these multiple differential equations to go from space to time and express space-time, what he did is he measured the length of all the power lines in light seconds. And by making his measurements in light seconds, instead of meters or centimeters or cycles per second or these things, what happened is then all of a sudden these two dimensional relationships unified, and Steinmetz was able to calculate and visualize and explain electric waves traveling in these phone lines and power lines that no one even knew existed. Most of this stuff will not even appear on the voltmeters in a lot of systems, and there's no way to measure it because they're existing in these various time frames going backwards and forwards in spaces. And Steinmetz came up with a much more advanced theory of electricity that unfortunately was never allowed to complete. But he started on it, and it's something to work with. So let's keep going here then. Where did we leave off? Okay, now we're going to go into this actual capacitance and inductance. So the phenomena of capacitance is a type of electrical energy storage in the form of a field in an enclosed space. This is what we've already seen in our ether diagrams. This space is typically bounded by two parallel metallic plates or two metallic foils on an intervening insulator or dielectric. A nearly infinite variety of more complex structures can exhibit capacity as long as there is a difference in electric potential or electric potential exists between various areas of the structure. The oscillating coil, or Tesla coil when we refer to oscillating coil, represents one possibility as to a capacitor of more complex form, and this is what we're getting into here because it's all going to lead up to Tesla. Okay, let's keep going. Okay, the perception of capacitance as used today is wholly inadequate for the proper understanding of this effect. Steinmetz mentions in his introductory book, Electric Discharges, Waves, and Impulses, to quote, and we've already gone through this about the electric charge, so let's keep going. Okay, we keep going. All the lines of magnetic force are closed upon themselves. All lines of dielectric force terminate on conductors, but may form closed loops in electromagnetic radiation. These represent the basic laws of lines of force. It can be seen from these laws that any line of force cannot just end in space. We've pretty much seen this graphically already, so let's continue. Faraday felt strongly that action at a distance is not possible through empty space, or in other words, matter cannot act where it is not. He considered space pervaded with these lines of force. Almost everyone is familiar with the patterns formed by iron filings around magnets. These filings act as numerous tiny compasses and orientate themselves along the lines of force existing around the poles of a magnet. We saw this in the picture further back. Experiment has indicated that a magnetic field does possess a fibrous construction. By passing a coil of wire through a strong magnetic field and listening to the coil output in a pair of headphones, the experimenter will notice the scraping noise, in other words, the sound of the lines of force breaking on the conductors. J.J. Thomson performed further experiments involving ionization of gases that indicate the field is not continuous, but is a fibrous structure. He presents this in his book, Electricity and Matter, in 1906. This is where he developed the concept of the electron. Okay, we keep going. Consider the space between poles of a magnet or a capacitor as full lines of electric force. Okay, we've already seen the pictures. These lines of force act as a quantity of stretched and mutually repellent springs. Anyone who has pushed together the like poles of two magnets has felt this springy mass. Okay, we've seen the figures. We've gone through all that. Consider the... Okay, we're going... Let's go back to the diagram. Let's go all the way back. Can we go back to the flux diagrams?
Sure.
Keep going. Okay, this is what we're talking about here. Is this diagram of attraction, and then the next diagram of repulsion. This is what we're for. So I'll read the text. We have to keep this in mind. It's hard to do stuff in a serial fashion, but so if we can move back to the... Okay, I think it's the next one. Okay, so now we're talking about, okay, in figure 1, the lines of force are more dense along AB between the poles, and that more lines on A are facing B than are projecting outwards to infinity. So in other words, the lines are in between the two objects. Considering the effects of the lines of force on A, these lines are in a state of tension and pull on A, because more are pulling on A towards B than those pulling on A away from B. We have what appears to be the phenomena of physical attraction. Now we observe from figure 1, notice how that the poles are like rather than unlike. This is the second diagram, where all lines pull A away from B. This is the phenomena of physical repulsion. The lines of force can be more clearly understood by representation of it as a tube of force or a long, thin cylinder. Maxwell presented the idea that the tension of a tube of force is representative of electric force in volts per inch. And in addition to this tension, there is a medium through which these tubes pass. There exists a hydrostatic pressure against this media, or what's called the ether. The value of this pressure is 1/2 the product of the dielectric and magnetic density, which are these terms we've already encountered. Then there is a pressure at right angles to the electric tubes of force. If through the growth of a field the tubes of force spread sideways or in width, the broadside drag through the medium represents the magnetic reaction to the growth and intensity of an electric current. However, if a tube of force is caused to move endwise, it will glide through the medium with little or no drag as if little surface is offered. This is the opposite type of wave to the electromagnetic wave. The first one, sideways movement of the lines of force, is like moving a sail through the atmosphere. There must be a reaction. So if the dielectric lines of force represent the sail, if it's moving sideways through the space, then the air movement represents the magnetic reaction, and the energy of the entire system then can be called electromagnetic in analogy. But if the lines of force, if the sail is made to move sideways, there is no drag through the air, there is no velocity of light, there is no magnetic field, and now we have the world of Nikola Tesla. This is the type of transmission he was using.
Well, the reason I wanted to ask about the frame drag aspect of a rotating planet like Earth, because I would theorize, based on the model you're presenting, which I think is interesting, that the density patterns of the ether would be different at different parts in the Earth's surface. You would have a radically different ether pattern at the equator, than you would at the poles. I was kind of wondering if that in some way fits into the...
Well, see, unfortunately, these things have never really been worked out. That's why they gave up on the ether.
But nonetheless, I mean, if an experiment were to be designed with this idea in mind, would that be one of the things you would want to look at?
Well, obviously, the thing is to try to get a better understanding of how this all relates to, is the ether more dense in one part of the solar system than the other? The question has always been asked, is the ether carried with the Earth, or does the Earth move through the ether? And then the thing is that the ether being physical at all, is there's no way to pinpoint it. All of these people, as you find in Whitaker's book, for the hundreds and hundreds of pages, came up with all these models of the ether that couldn't possibly work.
Michelson Morley showed that too.
Right. Everybody came up, that's why this guy Lamour stated that let's just drop trying to say what the ether is, because we have all the interrelations handed to us through observation of electric phenomena. As Heaviside said, why should I not eat my dinner? Because I don't understand how I digest it.
When the tether was towed behind the space shuttle and it went poof, I'm kind of curious, how do you see that as fitting into this framework of reference? Remember the tether that was towed behind the space shuttle?
Yeah, they were trying to drag a capacitor, right? Or a ball or something?
Actually, they were kind of unclear as to what they were trying to do. But the theory was they were trying to see if they could actually collect voltage from the Earth.
Well, obviously they did.
Well, they did. but the fun part was they got much more than they thought they were going to get. I thought that might be sort of interesting.
Well, the thing is now you have to remember when you get out in outer space, the rules seem to change quite a bit, but this stuff doesn't, they don't tell you that. For example, you can't see the sun or the stars in outer space. You can see the moon, you can see your hand, you can see the spaceship, you can see rocks, but you can see the planets, but you can't see the sun and you can't see the stars. So there's something about, there's a primary light and a secondary light, and then you have to figure what kind of voltage gradients exist between the Earth and the sun when Tesla says the sun is charged with 2 billion volts of electricity. The whole of the solar system, and it's the only way to explain how a planet like Pluto, because a large number of planets are lining up right now. And what this does is this causes solar flares. Okay, the physicists, you tell that to the physicists, particularly an astronomer, they'll be twitching on the floor, puking their lunch up. But nevertheless, this is well known by all RCA engineers, and it doesn't matter what physicists think, because all RCA cares about is money. And if the transmitters don't work, then the money gets cut off. So what RCA found is that planetary alignments influence the solar flares and the electrical conditions of space and cause these massive changes in radio propagation that go beyond anything you can explain with aurora borealis, or because I studied this stuff for a long time at Sonoma State with all the RCA equipment, and there's something much deeper going on here. If you look at the planets as elements of a capacitor,
and there's electrostatic lines of force between all of these planets, then it seems to make sense that if they move into configuration, the lines of force will be able to join up better. And it's also a condition of capacitance, as we'll get into some of it here, is if you take two objects which have an electrostatic field between them, and the more you try to separate them, because they mechanically want to pull each other together, the more you try to separate them, the higher the voltage has to raise in order to keep the quantity of energy constant, according to the law of conservation of energy. And the voltage will continue to raise, and this is how lightning is formed, until eventually nothing can withstand that stress, and it blasts. So this is going on in outer space, and somehow, as a friend of mine said, NASA is abbreviation for never a straight answer.
Well, actually, okay, that's a very good answer. But you do have a comrade, and I'm sorry I can't remember the name now. Somebody here probably knows it. There's a guy who wrote a book called The Electric Universe. And
Yeah, I'm trying to communicate with him, but he doesn't seem to be interested in anything I'm working on.
But your whole idea of the planets lining up,
Right.
essence, I mean,
Well, it's not my idea. It's kind of the idea. I'm not really creating any of this. I'm just taking all the pieces and putting them together. I'm just kind of, they told me in high school that I was retarded. So I'm just kind of, a homeless person that just takes books and pastes pages on, other pieces of paper in the public library.
I was accused of this. It's okay.
But let me get back to this because I don't want to lose track of our concept. So we're talking about lines of force and capacitance. So much of the mystery surrounding the workings of capacitance can be cleared by close examination of inductance and how it gives rise to dielectric phenomena. So basically what I'm saying is our knowledge of magnetism and inductance is farther than the knowledge of the dielectric and the capacitance, because the physicists say there is no dielectric and there is no capacitance, that it's electrons. And it's action at a distance. There's no lines of force in between. It's electrons and there's no electricity. It's matter. But this is a grave mistake, and this is what we're going to climb out of. Okay? Inductance represents energy storage in the space as a magnetic field. So if we look at all those lines of force around the magnet, that represents the storage of energy. In other words, there exists there in that field the force keeping it alive, stored electrical energy, just like a bottle in that magnetic field. The lines of force orientate themselves, as we've seen, in closed loops surrounding the axis of current flow, which is basically a shadow of the magnetism. It's the magnetism scraping on the wire. That's what we call current flow. The larger the space between this current and its images or reflections, that, in other words, the wire on the other side, the more energy that can be stored in the resulting field. So, in other words, the bigger the space between the wires, the more space we have, the more outer space we have, the more magnetism we can hold in that bottle. It just makes absolute physical sense. Let's continue. The process of pushing these lines or loops outward, causing them to stretch, represents storing energy as in a rubber band. A given current strength will hold a loop of force at a given distance from a conductor passing current, hence no energy movement. The situation stabilizes itself. If the flow of current increases, the energy absorbed by the field, I can't read it, can someone read that for me? Or can
Absorbed by the field
as the loops are then pushed outwards at a corresponding velocity. Because the energy is in motion, an electromotive force must now accompany the current flow in order for it to represent power. The magnitude of this electromotive force exactly corresponds to the velocity of the field. As we've seen, a change in magnetic field with respect to time is voltage or electromotive force. So as long as there's change in the magnetic field, there must be an electromotive force. A model would be is if you're flying down the road at a constant velocity in your car, you feel no motion. You're not being pushed forwards or backwards. But as soon as that velocity varies with respect to time, then all of a sudden there's an inertial response where you either are pulled forwards or pulled backwards. This variation in velocity, the rate of change of velocity, where velocity is analogous to magnetism through the swirling of the ether, the electromotive force results as a reaction to any type of change in that system, just as inertia. In fact, we call inductance in electronics electrical inertia. So in the motion, an EMF must accompany the current flow in order for it to represent power. The magnitude of this course, we've gone through that.
If the current ceases changing in magnitude, thereby becoming constant, no EMF accompanies it, as no power is being absorbed. However, if this current is decreased, and represents then a negative velocity of the field as the loops contract. Because the EMF corresponds exactly to velocity, it reverses polarity and thereby reverses power, so it now moves out of the field and into the current. Since no power is required to maintain a field, only current, the static or stationary field represents stored energy. Okay, we'll move to the next page. Any interesting features of inductance manifest themselves in the two limiting cases of trapping the energy or releasing it instantly. We call these the limits of zero infinity. In other words, time equals zero, or time is instantaneous. In other words, there's no time to grab onto. When it is switched off, the inductance drains its energy into the resistance that converts it into a form of heat. We will assume a perfect conductor that has no resistance. In other words, we have a coil or a system that's cooled to absolute zero, let's say. If we remove the current supply by shorting the terminals of the inductor, we've isolated it without interrupting any current. Since the collapse of the field produces EMF, this EMF will tend to manifest. However, a short circuit will not allow an EMF to develop across it, as it has no resistance by definition. No EMF can combine with current to form power. Therefore, the energy will remain in the field. It will be trapped. It will be closed. The door will be closed by the wire tying the two ends of the coil together and forming a complete circuit to a loop for the magnetism to be trapped inside. And the experiment of this is you take a piece of lead cooled to absolute zero and drop it in the liquid helium that's cooling it to absolute zero in a magnet, is it will float on the magnetic lines of force, because now it's become a perfect conductor, which is not true. It's a perfect obstructor, like Heaviside says. The magnetism cannot get into the counterspatial or interdimensional material of the metals because of the absolute zero and cause electron flow. So the so-called conductor will float on the magnetism because there can't be any change in the energy balance. So you have like a type of magnetic shock absorber or spring. It can't fall down because the magnetism will hold it up or exactly what we're talking about here. Any attempt to collapse the field increases the current, which pushes it right back out. This is one form of storage of energy. Okay, now we're going to go on. Okay, now we're going back to our fields. This is where our energy actions are, is in this field. Let's keep going. We're going back to our fields again. So this is the space we're in. Okay, now, very interesting and dangerous phenomena manifest themselves. This, particularly when you're working on DC ships, this is something you really have to watch out for. Manifests itself when the current path is interrupted. In other words, if you break the circuit wide open, like one of those vacuum switches tried to do on the substation disconnects. In this case, the resistance is best represented by its inverse conductance. The conductance is then zero. Because the current vanishes instantly, the field collapses at the velocity approaching that of light, theoretically. That still hasn't been measured. As EMF is directly related to velocity of flux, it tends towards infinity. Very powerful effects are produced because the field is attempting to maintain current by producing whatever electromotive force is required. That's what starts feeding these flames on the switches. If a considerable amount of energy exists, say several kilowatt hours, that's what you use in your house in one day, or 250 kilowatts for a lightning stroke. A lightning stroke has 250 kilowatt hours, or 250 units of energy that we're dealing with here. The ensuing discharge can produce most profound effects and completely destroy adequately protected apparatus. So if, let's say, I have a 50 horsepower DC motor and has these giant inductance coils in it to create magnetism. Now, if I go into the contactor box, I find this big resistor in there. And what it's designed to do is when that contactor opens up and tries to disconnect the inductance from the rest of the bounding electrical system, the collapse of the magnetic field will generate whatever voltage is necessary to keep jumping across those contacts, and it will leap out and kill you.
I have to stop you for a second.
Whatever voltage is necessary to keep jumping across the magnetic field, which represents stored energy, and try to stop the field from existing, or whatever voltage is necessary So they put these drain resistors inside the motor starting boxes to absorb that blast so the magnetism can release itself in a sane rate. So this is something in DC you have to deal with this situation. And what will happen is if you break the circuit instantly, we'll get it. If you can't do it, it gets into another process inside the windings that will prevent it from going to infinity. And that's what we're going to go into next. The magnetism, the energy has to go somewhere and finds another route. So let's keep going. So now we have another form of energy storage to try to absorb this up, and that's the capacitance. Okay, through the rapid discharge of the inductance, a new force field appears that reduces the rate of inductive electromotive force formation. This field is also represented by lines of force, but these are of a different nature than those of magnetism. These lines of force are not a manifestation of current flow, but of an electric compression or tension. This tension is termed voltage or potential difference, and these are our dielectric lines of force. So the magnetism will produce an electromotive force to try to maintain the current flow, but this electromotive force will then create a dielectric field, and this ultimately limits the situation so it doesn't go to a trillion volts. Usually in a big motor, it'll limit off at about 10 or 15,000 volts, but usually it'll blow holes in the windings. So let's keep going. Unlike magnetism, the energy is forced or compressed inwards rather than outwards. In other words, we're going into a counterspatial relationship. The electric lines of force push inwards into internal space and along axis, rather than push outwards broadside to the axis as in a magnetic field. Because the lines are mutually repellent, certain amounts of broadside or transverse motion can be expected, but the phenomena is basically longitudinal. This is, we're getting into Tesla's world now. This gives rise to an interesting paradox that will be noticed with capacity. This is that the smaller the space bounded by the conducting structures, in other words, the closer the wires are together, or the closer the plates of the capacitor, the more energy that can be stored. So it's defying our concept of a bottle holding energy. In other words, in this case now, the smaller the bounding structure, the more dielectricity will hold because it's being held in counter space. So the electric field, let's go back to the electrical field diagram. Okay, so these magnetic motions or velocities, okay, and these dielectrics are referred to more as torque or compression. The magnetic lines of force exist in outer space. The dielectric lines of force exist in inner space or counter space. So the electric field in between transmission lines or telephone lines or coaxial cables or any of these things represent the storage of energy in two different aspects of the dimension of space. So in other words, we could say in physics terms that there's two dimensions of space that we're dealing with here. Outer space and inner space, and these have the independent ability to store electricity, which is in there in actuality because it will either shock you or it will burn something out or it'll explode or it'll light up a light bulb or whatever, it's there. Okay, let's go back. Okay, now where did I leave off? Okay, I need to go a little further. We're in capacitance or inductance. Do you remember? I don't know where we're at.
Wait, we're at 13.
What's that? What number we're on?
13.
13? Okay, let's go back to 13. Okay, there we go. So the smaller the space bounded by the conducting structures, the more energy that can be stored. This is the exact opposite of magnetism. With magnetism, the units of volume of energy can be thought of working in parallel, but the units, volumes of energy and associated with dielectricity can be thought of working in series. So magnetism tends to deal more with the square area type of space storage, where the dielectricity is more the space in between the lines on the ruler, which can keep getting smaller and smaller, where this one keeps getting bigger and bigger. Okay, let's keep going. With inductance, the reaction to change of field is the production of voltage or electromotive force. The current is, or magnemotive force is what we're talking about current. We're also speaking of magnemotive force. We have to go back to our original relationships, but like I can't jump so far so fast. The current is proportionate to the field strength only and not the velocity of the field. With capacity, the field is produced not by current but voltage. This voltage must be accompanied by a current in order for power to exist. The reaction of capacitance to change of applied force then is the production of current. So where the magnetism's reaction was voltage or electromotive force, the capacitor's reaction is current or magnemotive force. So the inductance reaction of electromotive force creates a potential to charge the capacitance, but the capacitance reaction creates magnemotive force, which tends to feed the inductance. So we have energy trapped in a self-denying situation where one storage is the antithesis of the other, and the energy can never stay put. It has to constantly go back and forth. That's how we get our frequency. If we go back to the time equation, this is what determines the frequency, is it has to go back and forth. It has nowhere to go, and it can't stay put. So let's see, I left off. The current is directly proportional to the velocity of the field strength, just like with magnetism. When voltage increases, a reaction current flows into the capacitance and thereby energy accumulates. If voltage does not change, no current flow, and then the capacitance stores the energy which is produced in the field. So we stored the energy in the coil by tying the two leads together, but we stored the energy in the capacitor by taking the two leads apart. So then if we look at coil and capacitor together, one is closed and the other is open, and we can see how this denial process starts this exchange. It's like an antithesis that can't get out of its loop, and it has to occur at a definite frequency.
So the frequency is the third dimension then?
Well, no, frequency is a time dimension where the inductance and the capacitance are geometrical proportions. Spatial geometrical proportions. They have no real dimensions in their own being. They're more, well, I'll get into that later, what the dimensions of these things are. Okay, so where did I leave off here now? If the voltage decreases, then the reaction current reverses and energy flows out of the dielectric field. As the voltage is withdrawn, the compression within the bounded space is relieved. When energy is fully dissipated, all of the lines of force vanish. So what we've seen is when we discharge the inductance by breaking the circuit, in order to keep the situation in the realms of reality and not infinity, the dielectric field had to take all this up. So in these paragraphs, we've seen how energy is basically moved out of the magnetic field and into the dielectric field, and then the reverse situation can bring it right back. Let's go further on. Because the power supply which provides the charging voltage has internal conductance, after it is switched off, the current leaking through the conductance drains the dielectric energy and converts it to heat. This is just like the resistance did in the inductance coil. We will assume perfect capacitance having no leakage conductance. In other words, in the inductor we had perfect conductivity or zero resistance, and in this case we have zero conductance. In other words, we have perfect insulators. We open circuit the terminal as a capacitor. No path for current flow exists by definition of an open circuit. If the field tends to expand, it will tend towards the production of current. However, an open circuit will not allow the flow of current as it has zero conductance. Then any attempt towards field expansion raises the voltage, which then pushes the field back inward, so it's trapped. Therefore, the energy remains stored in the field. This energy can be drawn for use at any time. It's another form of energy storage, which exists in a conjugate relation with the storage of magnetic energy. So we keep going. Phenomena of enormous magnitude manifest themselves when the criteria for voltage or potential difference is instantly discharged. This is how Tesla managed to create a special type of oscillating and impulse currents that he used in his technology. We'll see about these later. The effect is analogous with the open circuit of inductive current. Because the forcing voltage is instantly withdrawn, the field explodes against the bounding conductors with a velocity that may exceed light. Because the current is directly related to the velocity of the field, it jumps to infinity in its attempt to produce a finite voltage across zero resistance. If considerable energy has resided in the dielectric force field, again, let's say several kilowatt hours, like in a household daily use, that quantity of energy, the resulting explosion has almost inconceivable violence and can vaporize conductors of substantial thickness instantly. Dielectric discharges of great speed and energy represent one of the most unpleasant experiences the electrical engineer encounters in practice. When you're dealing with these giant phase-advancing capacitor banks in these substations that connect the grid together, is if those things stay charged, is if you don't drain them through a resistor, but you try to short that thing out, the blast will just basically blow your eardrums right out and blind you. That's the energy of a capacitor is nearly instantaneous, and it tends to be more of a retarded type of phenomena. This one doesn't slowly build up. This one slowly builds down. Okay, so let's go on. No, back one.
Next one.
The powerful currents produced by this sudden expansion of the dielectric field naturally gives rise to magnetic energy. The inertia of the magnetic field limits the rise of current to a realistic value. The capacitance dumps all of its energy back into the magnetic field, and the whole process starts all over again. The inverse of the product of the magnetic storage capacity, which we call inductance, and the dielectric storage capacity, which we call capacitance, represents the frequency or pitch. In other words, the rate at which this energy interchange occurs. This pitch may or may not contain overtones or harmonics, depending upon the extent of the conductors bounding the energy. So this basically, this part here on the ether is complete. We'll have you answer. Lucy, I got enough time. We'll have you ask questions on this now, if anyone has any questions. No questions?
I'll offer a comment.
Okay.
When we were developing power supplies for some of the particle beam weapons that we were playing with many years ago, this idea of giant capacitor banks discharging in essentially near real time was quite well demonstrated.
Yeah.
We blew things up all the time with that very principle, so I can testify.
Okay. Well, I can't believe nobody has any questions on something this... everyone understands everything I'm saying?
Oh, that's a big thing.
How many people understand 10% of what I'm saying or more? Okay. I think everybody's getting something out of it, though.
Oh, yes.
Okay. Well, as long as I'm not putting everybody to
Well,
sleep.
let me throw one question out since we're talking about this kind of stuff. What if you had the potential for time phase shift, even very slightly? You would then perturb dramatically, I would think, the energy quotient potential that's given reference point in this model. Possibly?
Yeah, that's what, remember when I went back to the, I don't know if we can go back there or not, but when I showed the dimensions of resistance were inductance varying with respect to time, and then I showed the dimensions of conductance were capacitance varying with respect to time, that's a time shift. And what that does is then energy starts to go sideways into a dimensional relationship where it's no longer energy. Its pieces may still be there, but it's no longer, the pieces no longer make the pie, which we call energy.
Right.
Instead, we just have the can of cherries and we have the bag of flour. They're all still there. They haven't gone anywhere. You can take energy, okay? Now, according to Heaviside's law of the continuity of energy, that energy that exists in this capacitor coil can vanish as long as it exists in another time. But that still meets the requirement for the law of continuity of energy. So this is basically how we get energy synthesized in electrical systems, is by moving it around in time. That's where an alternating current phase is always the number one word in everything we're dealing with, is where are you at in the cycle? And you can build electrical machines to do this. I've seen them where energy will go into a generator, okay, and the generator will have no load connected to it, okay, and you can have a kilowatt meter, okay, sitting on the input of this generator. Not an amp meter or voltmeter, won't give you the real energy flow. It'll give you a false reading. But if you have a power factor corrected kilowatt meter, or I haven't done it with a kilowatt hour meter, that would have been the proper way to do it. Energy will go into this rotating machine, which varies with reluctance with respect to time, such as an Alexanderson alternator, and the energy will vanish. You will be yanking power and paying for it from the utility company to make this thing spin, and the energy is not heating the bearings up. It's not making windage. It's not coming out of the shaft, out of the wires, or the energy is simply taken apart, by causing this time shift in the magnetic cycle in the 60-cycle alternating current field.
Well, given that, that's why I want to get back to this frame drag stuff, because time has been shown to be a non-linear dimension that's been proven. And furthermore, since you can go to different parts of time, space, and find elasticity or compression, that would suggest that the harvesting of this energy would be different in different locations, or those densities are different, because the time elongation or compression would be different.
Well, but in this theory, those things are it's not expressed that way. In fact, it's deliberately avoided to express things that way. Because you can't really distort the dimensions of time and space because they're metrical dimensions. But let's get into a little more. Okay, if we have dimensions that are called quantitative dimensions, and we have dimensions that are called metrical dimensions. I wasn't going to read this. The dimensions of space and time are dimensions of measurement. The measure of how far, the measure of how long, space and time are metrical dimensions. These conceptual dimensions are not those of a concrete physical or electrical reality, but are rather a sort of mental process. So the ideas of distorted time or space basically just says that you're building clocks that are distorted and you're building rulers that are distorted. In electrical engineering, it's considered a laugh. That's why I'm making sure to reinforce these concepts, because this is very important in electrical engineering, otherwise you won't get it.
Are you saying that relativity, general relativity, doesn't hold then?
Yeah. Basically, it's just a way to explain away electricity and eliminate it. I actually think it was a conspiracy. Well, if Heaviside painted his fingernails pink and slept on concrete blocks, maybe not everyone went along with it. But we already heard what Tesla had to say about it. I mean, the whole beginning of the book was filled with horrible Michael Savage stories and everybody all disgruntled. So maybe I'm not just making this up. Because if you want to understand Tesla, you better get all this stuff out of your mind, or you're not going to get one iota of understanding of how Tesla works. You'll be permanently blocked from understanding it. That's my theory of why there's the theory of relativity. But we're not here to talk about the theory of relativity. We're here to get away from it. Okay, now conversely, the dimensions of mass or magnetization are concrete realities. These exist independent of the metal process. Hence, these are called the quantitative dimensions. These are what we apply space. These are what we apply to. We have a number of grams per square centimeter, per cubic centimeter. We have the number of volts per second, or any of these type of things. It's always the metrical dimension is attached. That's why we started with the undivided quantities, and then we metrically worked them in time to produce power and voltage, and we metrically worked them in space to produce flux densities over areas. Hereby it can be seen that the metrical dimensions work upon the quantitative dimensions so as to gain a mental concept of the process or actions involved in the quantity. 4 electrical dimensions are required for electrical representation. One is the total magnetic induction. The other is the total dielectric displacement. Our metrical dimensions are time and space. So our 4 dimensions are phi, psi, and then L for length, and T for time. These are the 4 dimensions of electricity. Everything in electricity consists of an interrelationship of these 4 dimensions. In physics, it's mass, temperature, length, and time. In electricity, it's magnetism, dielectricity, length, and time. It's a completely analogous relationship to physics, but it exists in a different reality. Let's take a situation of the gas laws, which we went back to in the beginning. I wanted to draw this up, but I didn't have time. Maybe we can do this here. Can I move? Yeah.
Yeah, absolutely.
Let's, does this paint work? Let's see. So if we have pressure, okay, pressure basically increases with temperature and decreases with volume. So these 3 quantities always have to exist in a relationship. Okay, now if I take a cylinder, okay, and I have gas trapped in here, okay, it has to correspond to the kinetic theory of gases, which this describes. So if I have a constant temperature, if I have a pressure of a certain quantity in here and I have a temperature of a certain quantity, if I decrease the size of this container, then in order for this relationship to preserve itself, either the temperature has to go up or the pressure has to go up, and consequently, both of them go up. Okay, now if I take a given cylinder and I put a fire under it to raise its temperature,
Okay? The pressure will go up and the temperature will go up, but the volume can't go up. So we have here a situation where these three quantities have to be conserved. Now, you brought up the time factor. Well, this is interesting because this is the important part. Now, if I make this part that we blocked off in this cylinder a piston in the engine, okay, and I'm introducing a fluid situation in here, like gasoline, and causing it to combust, now we have a time cycle where these things are varying, and it causes what we're going to get into what's called a hysteresis loop. And that way the energy can go in or out of the system, and if you measure the pressure in the cylinder of an internal combustion engine, it will remain constant through the entire cycle. This thing about explosions, pushing the pistons, and all that's a bunch of gobbledygook like electrons flowing in wires. In actuality, the pressure will remain constant because the temperature and the volume are changing, and the ability to keep that pressure constant is what allows the oscillating time-variant cylinder to take the energy from the combustion and deliver it to the crankshaft. And there's various cycles that are called like diesel cycles and what have you. I don't know that much about engine theory, but this is the type of situation we're dealing with. So we have the normally time-invariant model, like if we have inductance and capacitance, we can represent that by this energy stored in here. But if we have cyclic changes in those quantities, if we vary them with respect to time, then we start to get out of these dimensional relationships and get into something more complicated, where energy either comes into the system or goes out to the system through some form of translation, either from the ether or from the burning gasoline or whatever type of situation. This is basically what we're trying to get into theoretically, so we can figure out how to produce these electrical systems that tend to be self-sustaining rather than so dissipative, like the power line between the shipyard and the substation. That power line was creating electrical energy because of the fields that were going backwards in time and space out of the shipyard back to the substation, took that electric field and rephased it and turned it into production of energy rather than consumption of energy. So let me get back to the, so that's what we're going to try to get into now is more of the mathematics.
Were those lines to the shipyard dual paired lines?
It was 600 amp, three-phase, 12,000 volt power line.
But were they like pairs of lines?
Yeah, they were big, heavy copper cables, two in parallel for each phase. Yeah, roughly probably, about 1,000 pounds of copper per span. If you ever stuck anything across those, it'd be the big blue flash. They'd be, I don't know if anyone's ever used acetylene torches, but when you don't give it oxygen, those little black flakes floating in the air, that's about all that's left after you tangle with 12,000 volt bus bars.
We've been talking for 2 hours, almost 3 hours. You want to take a 10-minute break?
Yeah, that'd probably be good.
Okay, we'll take a 10-minute break. You're ready. Okay, we're recording.
Thanks for to go to the first equations.
What I'm saying is so fascinating, you just have to hear it.
Let's go on let's go to the equation section now. Next one after this.
Attention, please.
The next one.
Next one.
Yeah. Keep going.
Down!
Keep going.
Oh, next one. Energy to matter.
Keep going. Keep going. So we see equations. Okay, these are the books that the stuff came from. We don't have time to really. Okay, there's basically what we've been talking about.
So I think we're on the last part now.
Yeah, now we're on the math. Now we enter the subject of algebra. In other words, what type of mathematics can we develop to talk about all these things and engineer them with pieces of copper and pieces of brass and wood? So you had that equation up there before we took a break. Are they gone?
Which one?
The next frame. We need to keep going.
Yeah, we're in algebra now, right?
Yeah.
Yeah. Yeah, it's
Does it take a while to load in?
yeah.
Oh, okay.
It's loading it right now.
Please, can you remind me where these notes came from? The story of these notes that you are sharing with us?
Whose notes?
What book is this?
Let me see.
You have a number of books. Which book is
Those
it?
points that I'm pointing until now, the notes that you have been going through.
Well, this one got all screwed up.
Yeah, I didn't quite,
I think NAM has entered the system.
yeah, the resolution of the screen on the drawing doesn't match the resolution here for some reason, so.
Let's go to the next one, see if it's all screwed up. Not too bad. Okay. So let's go back to the organ pipes. Was there anything before the organ pipes?
No, that's number one.
Okay. So the reason I'm showing this is now we're going to start to talk about algebra. In other words, the way to work with this in the engineering reality. You have to be able to calculate. So what we see here is we look at these rows of pipes, which all represent frequencies or wavelengths in what's called a geometric progression. You can see they don't increase at a steady rate, but they increase at a rate of proportionality that grows or decays. That's what we're looking at. This is what's called a logarithm, or an exponential type of relationship. Instead of 1, 2, 3, 4, 5, which is a linear relationship, what we're dealing with in studying electricity is a logarithmic relationship, more like 1, 2, 4, 8, 16, 32. That would be a logarithmic or an exponential relationship. So these curves are basically the curves that we're dealing with in our study of electricity, but these curves exist in the dimensions of electricity and not necessarily in physical dimensions such as we see with the organ pipes, but the principles are exactly the same. The curvature or the rate of change. What we're dealing with here is we have to have a mathematics which can express change. This was first developed by Newton and Leibniz in what was called the calculus, but the calculus is very unwielding for this type of stuff and a lot of times will not give you meaningful answers. So let's go to the next one. So the archetype of our equations is all based on this form called the conic sections. So if we move our plane of reference, we might call it, through this cone, we have circles, we have ellipses, and we have parabolas. But they're all based on the same form. They just represent a different angular displacement. And as we'll see later, this angle of the plane, we're going to call this in Steinmetz's terminology, the angle of hysteresis. And we'll see later how this comes into being. Let's go to the next one and get another shot of it. So we can see that our equations of the circle, which is the sine wave, or equations of ellipse, which is like a dissipating sine wave, or a parabola, which is kind of like a sluggish capacitor discharge into a coil. These are all direct, physical, producible situations with geometry, and these are what I call our archetypes that we build our engineering math on. There's these very simple relationships. If it was taught to you like this in school, you would be a mathematical genius after the first semester. But instead, what's that?
Is there some reason why you don't have hyperbolas?
That's next.
Oh.
That's what we're getting into. Okay, let's keep going. Okay, so that's another, okay, now we're going to keep going. We have another look at our cone. And these are the cross sections. So these are basically our cyclic or alternating current waves, which are based on circular functions. Let's keep going. The parabola is a crossing point now into another relationship, where we're getting out of the sine waves and we're getting into what are called transient or impulse waves. These are the types of waves that Tesla was using. He was not using sine waves in his later developments. He was using a completely different type of electricity, just as we saw with the flux lines. There's energy storage in outer space and there's energy storage in inner space. Tesla's technology dealt with the energy storage in inner space, where you're pulling energy from kind of the infinitely small and expanding it out into the presence of where we are at now. So let's keep going. Okay, now if we turn the situation sideways, we get what's called the hyperbola. Now the hyperbola is a type of circle turned inside out. And in this type of graphical presentation, we have to have two cones for the hyperbola, but ultimately we need two cones for the circle too, but this guy didn't do it in the book. Because in any type of alternating current or circular function, there's one wave that turns clockwise and there's one wave that turns counterclockwise. In other words, one's going forwards in time, one's going backwards in time. The inductance delivers forwards in time, the capacitance delivers backwards in time, and the two produce a resultant. With the hyperbola, these are like impulsive discharges, where there's no oscillatory exchange, but the energy is growing, like the switch is blowing up, or is decaying, like the resistor hooked across the inductance coil and eating its magnetic field produces these type of curves. But there's always a pair of curves, and we can say that if we have inverse dimension representations like minus time and plus time, then the upper conic would be negative time and the bottom conic would be positive time. But this stuff is very difficult to represent in the spatial representations when it really exists in time representations. But nevertheless, these are our archetypes. These curves are exactly what we must calculate when we're dealing with transmissions of waves down telephones and power lines and inside motors and generators. So let's keep going with some more. There's a side view of the hyperbola. It's a pair of curves that approach each other. And we could call this as an inside-out circle is what it is. This is a circle turned outwards into another relationship. We could call, in physics term, we would call this a circle in another dimension. An anti-circle. Let's keep going. There's another, the plane has shifted a little bit. Now we've moved our angle of hysteresis so it's cutting differently. And then he's got a really good shot here towards the end. There we can see our different types of hyperbolas. Okay, now we're going to start to get a little more abstract with this. As we move along, there's a parabola, and then of course if it turned sideways there'd be a circle that would just appear as a straight line. Okay, and that didn't show up, but that was a drinking fountain making a parabolic arch, showing that
You could show it with the laser.
I can see it.
Do you see it? Yeah, it's kind of there, yeah. Somehow this is all screwed up. It's a disaster. But at any rate, you can kind of see it. Okay, now we're dealing with it more symbolically, where there we go here, and we have our axis of angular movement, where we can go from the hyperbolic to the circular functions, and we get our equations where these things all basically are where two quantities always equal unity. In other words, just like the pressure, temperature, gas laws, is the sum of, or the product of, the sum of two quantities must always equal a constant. So we'll get a little further down into that with the next picture. So we'll take the circle. Okay, the circle always has a constant radius. No matter where it is, one thing we know is that R always equals 1. Okay, and the way that this part moves and the way this part moves, move it in such a fashion as we go around, one lengthens, this one gets longer as we go around, but this one gets shorter. So this one would be called the sine wave, and this one's called the cosine wave. So this is where our AC waves come from. Is as the generator rotor is turning, is these projections of voltage and current produce these spiral movements. It's like this thing is moving downwards, and as it goes around, it makes a spiral as it moves. So we have our basic mathematical relationships in this, where these quantities, if you take the Pythagorean addition of them, they must always equal 1. That's very important. All the mathematics that we're going to develop henceforth will all utilize the number 1. The number 1 can actually be used as a calculating mechanism of such ultimate simplicity it's beyond belief. This is what's called the Steinmetz method. So let's go to the next one. Okay, now we have the hyperbola, which is basically an inside-out circle. Now we have, instead of the sum of the two quantities, we have the difference of the two quantities equal unity. So it's a similar situation, but turned inside out. And as you can see, it still has a circle type of reality, but it's only in an expanded type of. It's very difficult to explain these kind of things. I've been working on it for years, and I still haven't come up with the final thing so you can really make it click in your head. But you can see that one goes outwards and another one is confined. So these variations are what are called aperiodic. In other words, they do not come round and round like the circle, but they go through a basic motion and then they're gone. They come and they go. These are what are called transient electric waves, where the alternating current waves of the circle are continuous electric waves because the rotation is constant and the unit vector is constant. So there's alternating current waves are a continuous wave, where these represent impulses that are discontinuous waves. Okay, let's go to the next slide. This represented by this graph represents the velocity of light. which must always remain constant. So that means that this hyperbolic curve, where this represents frequency and this represents wavelength, the product of the two must always equal a constant, which is the velocity of light. So like the circle, the hyperbola has a character to it that has to always equal a constant quantity, and that's what makes its shape. This also could be the Lorentz transform for the relativistic mass increase, and time dilation follows the exact same type of curve, a hyperbolic curve, where you approach something but you can never reach it. So in other words, if the frequency goes down and down and down and down and down, then by following that point along this curve, the wavelength has to get longer and longer and longer and longer until eventually when the frequency is down, the direct curve is zero, the wavelengths are of indefinite or infinite length. So we have this inverse proportion between frequency. The higher the frequency, the shorter the waves. The lower the frequency, the longer the waves. But they must always equal the velocity of light, and that forces them into this archetype of curvature or rates of change. So here's a basic example of the hyperbola in action. So let's go to the next. Okay, now we're going to, this is the Steinmetz symbolic method, and we're going to go, what I've done with the Steinmetz symbolic method over a period of about 8 years is I've extended it hundreds of times beyond what Steinmetz did, and made a whole system of mathematics out of it to describe all these other type of electrical situations. It's still a little on the preliminary side. It's what Heaviside calls experimental math. Heaviside pointed out that mathematics doesn't really have to be the tight-ass thing that it's normally presented, but you can experiment with it and make up your own mathematics as you go. As long as you can calculate your values from it, that's good enough. And if the mathematicians hate you, then we have an explosion at the shipyard. Okay, so we start basically, we have the number 1 as an indivisible unit. If we take 1 to the 1 power, or the first power, that equals 1 and can only equal 1. But we can work with this. If we take 1 to the 1/8 power, or we would say the 8th root of positive 1, we must have 8 roots by definition, even though all these roots equal 1. So what this does is now this starts to break into a polar type of relationship such as we find in electricity. So I can take the 8th root of positive 1 and break that down into the 4th root of positive 1 and the 4th root of negative 1. So they can either be represented as an exponent or under a radical sign, but they're both the same thing. So the 8th root of positive 1 divides us or gives us 2 poles, the 4th root of positive 1 and the 4th root of negative 1. The 4th root of positive 1 is our circular functions, basically. The 4th root of negative 1 is our hyperbolic functions. So now we've taken these 2 curves and we've begun to express them symbolically. So basically we have 8 roots. One of them is positive 1, one is negative 1. One is positive h, the other is negative h. One's positive j, the other one's negative j. Now this is the Steinmetz method. He uses +1 and -1 for DC, and +j and -j for AC, which almost every electrical technician or engineer has seen, is that you always add the reactance to the resistance, where the resistance is plus R, the reactance is +j times R. I got into this in my last talk. I was referring to how you use these things as operators. So basically, what we've done is we've extended the laws of addition and subtraction to have a more expanded or generalized meaning. So the 8th root of positive 1 gives us 8 poles of electricity. These we'll call the continuous, and these we'll call the transient. This is the electricity we use today. This is the electricity that Tesla used. Okay, let's go to the next one. We're going to break this down more. Okay, so here's our basic form. Okay, we start from the 8 and we go into pairs of 4s. Then we go further.
Next one.
Next one. Okay, so we already saw this. So here we have our 8 poles, because an 8th order equation has to give us 8 results. So basically what I'm doing here, if this Steinmetz symbolic form advanced, is this will allow us to solve an 8th order differential equation without going through all the nightmares, by reducing it to simple algebraic relationships, and we'll see how this works as we go through. or we will attempt to see, because it's going to be, if you thought it was thick before, it's going to get thicker now. So all I can do is just go over it. Okay, let's keep going. Okay, so here we have basically our four real elements, which we will call DC and AC. So this is our continuous waves, and that's represented by the fourth root of +1, and we go on. Then we have the fourth root of -1, which gives our four transient elements. So these are our impulse and oscillating currents, as we'll see later. So let's keep going. Okay, so now we break these down even further. So if we take and go one more step, and we take the square root of +1, then that gives us +1 and -1. Okay, so we've gone from these elements, and we see how that can be expressed symbolically. So the square root of +1 gives us our DC. In other words, this is the battery, this is the light bulb. Okay? The absolute value of these always equals 1. Okay, let's keep going. Okay, I think we lost one here, but these are the 8 electrical waves we're dealing with, okay? This is the DC, and this is the AC. But we have all these other electrical forms that are very seldom talked about until the switch blows up, or the transformer catches on fire, or the railway shuts down, and then Steinmetz came in and found there was all these other forms of electricity flowing that evaded the switchboard instruments and were very destructive. And Tesla found out a way to harness these into a new type of technology that is completely unknown, even though he told everybody and over again how it works. Everybody goes right back to DC and AC. But Steinmetz started this mathematical process now where we can show these things in their interrelation. So let's keep going. Okay, so this is the AC wave. Okay, so now the square root of -1, and we have to remember that GE said Steinmetz could create electricity out of the square root of -1. That was very close, but actually it's the square root of -1 to the square root of -1 power. Yeah, and that's what we're going to get into, which should be a nice Alice in Wonderland. Okay, let's keep going. Okay, so now if we break down more, if we take the square root of +J, then that gives us, starts to get us into what we call impulse currents. So now, let's go back to the AC wave. Okay, this represents the inductance coil, and this represents the capacitor exchanging energy back and forth. So the square root of -1 represents the storage and transfer of energy, where the square root of +1, the DC wave, represents more of the energy coming and the energy going. Now we go back to the impulse currents. These are the waves that tend to be transient, where they have single discharges, where a capacitor is discharging or a coil is discharging. So this would be the energy supply, and this would be the energy sink in that situation. But now we're dealing with hyperbolic rather than circular functions. Let's go back to the waveforms. So that would be about waveforms. That would be these two waves. This area here would give us, wish this thing would work. I think the batteries are going dead. These are our impulse current waves. So if this one is plus and minus 1, this one's plus and minus J, you should have 8 waves here. Okay, it seems like there's something extra, but let's just keep going. These are our basic impulse type of waves that we're dealing with. Then we go on. Now the square root of minus J, this gives us plus K and minus K. And of course, the absolute value of all these things always equals 1. There's no quantity here. These are simply what are called versor operators. They give us polarity, but they don't give us quantity. They're like plus and minus signs. In other words, if I take 1 and I add it to 1, I have 1 plus 1. But if I take 1 plus 1, but I put a minus sign in front of the 1 on the second part as an operator, then I'll have 1 minus 1, and that's what we're doing here. This is an extension of the process of plus and minus out into a polar relationship, where all these aspects of electricity exist in 8 forms. 8 forms of electricity in action in a generalized situation. This is what comes out of Steinmetz's symbolic method. So we have a way of dealing with these things with arithmetic instead of differential calculus. The effects are massive on what understanding you can gain by getting rid of these giant differential equations. Okay, let's keep going. Okay, and then basically 1 to the first power can be given as the absolute value, that's what the two bars indicate, and this is the absolute value of any of these 8 poles is 1. So basically, together, it's a unit. The whole thing operates as a unit, ultimately it's not separate. Okay, let's keep going. So we have, these are our basic poles. We have plus and minus 1 like on a battery. Okay, we have plus and minus J like between the coil and capacitor. We have plus and minus H, where it's capacitor going into the resistor, let's say. And we have plus or minus K, where these are oscillatory exchanges, where capacitor, resistor, inductor, and resistor exchanges both occurring. So we end up with waves that have, we go back to the transient waves again, the oscilloscope type diagrams. These waves are represented by a double movement, where these are just simply what are called single energy exchanges. These are double energy exchanges. And then later on we get into pairs of these and quadruple energy exchanges. To go back with the physical analogy of the automobile, let's go picture-wise, go forward. Go forward, yeah. Okay, so this basically is our 8 poles, all of which have a plus and minus relationship. In other words, K has plus and minus, H has plus and minus, J has plus and minus, and 1 has plus and minus. So there's always opposition in the two forms, and these represent energy exchange. So if we want to look at a situation of energy exchange in practice, okay, as we explained, if you're in an automobile and your velocity changes with respect to time, then all of a sudden these secondary effects like electromotive force and magnemotive force appear. So if you go down the road and you put on the brakes instantly so that the wheels, we're dealing with perfect situation now, the wheels come to a complete standstill instantly, okay, and they do not slide on the pavement. What happens is the car wants to keep moving forward. This represents the magnetic field. The car wants to keep moving forward, but it can't. What happens is the tires start to twist, okay, which represents the capacitors. So now all the energy of the mass of the body, which can't go forward, but it's being pulled forward anyway, now is charged up in like a spring action in the wheels, okay, which only can deform so far and they can't move on the pavement, okay? So the car pulls forwards and charges up its energy, but now the inductive energy is all gone and is charged in the dielectric energy, symbolically, in the wheels. So what it is now the wheels, there's nothing holding them forward anymore. So what they do now is they pull the car back. As they pull the car back, they tend to restore to their original position, but at this point, now the car is flying backwards just as fast as it was going forwards. So what it does is now the wheels are distorted backwards in an equal amount, and the car moves backwards the exact same amount it moved forwards, and then again the whole process starts over. So the car, that's what causes the whiplash when you stop in the car. It's this oscillatory energy interchange produces, let's go back to our waveforms, produces this. The energy's trapped, and the car will just sit there and bounce back and forth forever, but nothing's perfect. So in reality, we don't get an alternating current, we get an oscillating current. Now how does this come to be? What it is let's say you slam on the brakes, but now, as we know, the car will skid. Okay? Now, if we go by electron theory tells us that the car's not moving down the road, but the road's moving, carrying the car. Now we know that's a bunch of crap. The road doesn't move, the car moves. Okay? But the relativist only sees the tire tracks and doesn't see the car, like the footsteps of the snowman, or the invisible man in the snow. The man is not there, because you can't see him. All you see is the footprints, and that's all that's real. But obviously that's not correct in our physical analog. So what happens is now, if the road does try to move, in other words, if the car slides on the pavement, it pulls the pavement forward with it, but the pavement lags behind the car. Now this is what the electrons do in the wire, and they get hot. The road gets hot and it makes a screech, okay, which is a disruptive type of oscillation akin to one of these type of situations. It's not a pure tone. It's a breaking, pulsing type of sound. That's what gives it that horrible sound. So what happens is before the wheels can completely absorb all the energy, the car has slid forward and destroyed some of that energy, so the oscillation will die off like this. Now if that rate of energy dissipation is so great that it can't reverse, then we get what's called the deadbeat impulse. So the car basically lurches forward and then kind of comes back and comes to a stop. So this is basically the physical representations in physical world realities that everybody experiences on a daily basis. This is the type of dynamics we're dealing with. It is no more complicated than that, other than you cannot see the electrical phenomena, but you can see the car and you can see the wheels. Okay, let's keep going back to the math. So these basically are just symbolic ways of saying these are the axes that we are operating in and the dynamics that result from it. It's no more complicated than that. It looks complicated, it seems abstract, but it's the ultimate simplicity when you're dealing with electrical calculations. Okay, let's keep going. Okay, so we have our 8 relationships, and we saw on the previous page that we can take each one of these letters and associate it with specific electrical waveform that's encountered in practice. Okay, we'll keep going. Okay, now I wrote a paper on this that I was going to present here, but there's no time for it because I have to warm you up with all the previous material, so we're just going to fly through it. Now, this is an example of the Steinmetz method. Let's just go from page to page. We start with the basic AC problem. Okay, we have a voltage across a resistor, and we have a voltage across an inductance coil, or a reactor, in this case a reactance X. Now if I add the voltage, if there's 1 volt across the resistor because of the back EMF, and there's 1 voltage across the inductor because of its back EMF, I do not have 2 volts as a result, because I have to add these in a Pythagorean right angle relationship. So instead of 2 volts, I have the square root of 2 volts. So basically, R and X, the R in ohms and X in ohms exist where this one exists in plus and minus 1, this one exists in plus or minus J. So this is the first use of this type of thing. So I would say R plus JX equals Z. Instead of R plus X equals Z will not give me the right answer. I have to say R plus JX gives me Z, and that's what the dot on top of the Z means, is that now it's a complex quantity. It's not a result of direct addition. But if I take these 2 quantities and square them, and take the square root of them, that gives me the length of this. And if I take the ratio and take the trigonometric function of it, then that gives me the angle. So this is the basic way that electronic technicians, not electrical engineers in general, but electronics technicians tackle the problem in this manner. So let's go on. We'll keep going. Keep going. We don't have time to talk about this. Okay. So we're going to represent this now. Is typically it can be called 2 quadrature planes. In physics it's called, I think, orthogonal, or there's a name they use that not normally used in electrical engineering. Can you help me with that, Charles?
Orthogonal's right.
Okay. What's that?
Orthogonal will do fine.
Okay. So we have the plane of resistance and the plane of reactance, but in reality we can't really present it like that, because they exist in 2 different type of dimensional realities. One represents energy storage, and one represents energy dissipation. So basically, the reactance has real physical existence in a magnetic field, but the resistance works in a strange way inside the atoms and destroys or creates the electric field, but it's not the electric field. But we have to add these 2 quantities to get the total voltage in the circuit. So we need a better way of visualizing it. So let's keep going. So let's take this plane of paper, okay, and we take the one that's at right angles and we turn the paper, so now that one piece of paper is broadside to us, the other one, because it's infinitely thin, we can no longer see it. So we call that the resistance, okay, or the imaginary plane. And the reactance is real because it'll light a light bulb, which is the resistance. So we'll call that the real plane, and we'll give that area, which is the dimensions of inductance, length squared. So that is a real quantity. Now we'll go one step further with this analogy, and so we can work with it geometrically. Keep going, next step. Okay, being that these things exist in time, all these calculations are in time, we can't have a surface of time, because time only exists as plus and minus, not multiplication. So what we'll do is we'll go take the plane and turn it again, okay, and reduce the resistance to what's called a weighted point, which has no physical existence in the equation, but is a point with weight. I think a guy by the name of Grossman introduced this idea in the 1800s. Okay, and we'll represent the reactance, which is the magnetic field, by a line because it has magnitude, which represents the quantity of energy in the system. And this gives us a kind of dimensional picture of the problem we're dealing with, and this is what makes it hard to visualize and work with in engineering. So that's why we have the Steinmetz method, because we can't properly draw the diagram. Let's go back to the XR diagram. Let's go back. Go back. Okay, well, we can use this as a calculating tool. In other words, you can go into your electronics test, and all you need is a ruler, okay? And you can measure 1 volt is 1 inch, and 2 volts is 2 inches, and draw a square, okay? And then measure that square, and then measure with your ruler, and get the voltage. I used to use this system in the Navy to pass the test, and I passed the test so quick by using this method instead of trig tables and slide rules that they accused me of cheating. Okay, let's keep going. But when you're a kid, you learn how to do things that maneuver quicker than they do in the adult world. Okay, keep going. Let me get some more pictures here. Okay, so these are basic alternating current representations. So if I start off, let's take the resistance R as our reference point, which is typically done in electrical engineering, because most of our consuming devices are resistances. They destroy energy. So they take energy out of the dimension, which we represented by this dimensionless point. Okay, now if I multiply by J, okay, or go around a right angle, okay, then this is what we call reactance. So if I go backwards in time by 1/4 turn of the rotor and the generator, okay, then in the time cycle, we've now entered reactance. Okay, now if I multiply by J squared, then we go around, then we have the opposite. I don't know what's going on with this thing. It's sure playing with me.
Almost put it in your eye.
See if I can try it.
Now it wants to go out. There's something, oh, it doesn't like the black. Okay, so if I go around, if I multiply a quantity by J, I've gone this far. J to the first power. If I go J to the second power, okay, now we're at the point where the energy is being produced, where here the energy is being consumed. So if this is the resistor, or this is the motor, let's say, that's eating the power, then this part of the cycle is the generator, which is producing the power. Now, in any rotation of an alternating current machine, it must pass through all 4 of these cycles. So there's always a point at which a generator is a motor, and there's always a point in which a motor is a generator. There's no separating these things. So we have the J cubed, then brings us the 3rd rotation, and then J 4th takes us back to J to the 1, and brought us right back to where we started from again. So we're developing a multiplication table. So we'll let this counterclockwise rotation represent the magnetic field or the consumption of electrical energy. And then we have the we'll do that in amperes and ohms. Okay, now let's go to the next one. Now we're going the other way. Now this is, we're not using Mohs anymore, we're using Siemens and volts. So now this represents more the capacitive side of what's going on. And it exists in the exact opposite, because this energy is always bouncing back and forth between these 2 fields. So now we have the conductance, and then we go around, and that gives us the susceptance of the capacitor, which is the inverse of the reactance of the inductor. And then we, this would be J to the -1 power, and then we have J to the -2 power, then that takes us backwards. We're producing rather than consuming energy. Then we have J to the -3rd power. It's dead.
Does anybody else have one?
Okay, it works, but it won't work on the paper for some reason. It just,
Repeat that again, please.
by using 1 to a fractional power, like 1 to the 1/4 power, as we've seen earlier, the 4 poles, or the 4 solutions to that power, represent each one of these 4 aspects of every alternating current electrical cycle. This is the Steinmetz method of representing alternating current, so that we can add and subtract in these conflicting or quadrature or conjugate realities, like one being dielectric and one being magnetic, or one existing as a field and one existing out of the field. It is these relationships. In order to add everything up in the equations, you have to have these operators that extend us beyond the original laws of addition and subtraction, because now we have to add in all these different forms that don't necessarily directly add. Okay, go to the next. Go back. So basically, in any alternating current cycle, we have the half where the magnetomotive force, where the amperes live, and we have the other half where the voltage or the potential and the dielectric forces exist, and these represent the watts or the energy exchange through the alternating cycle. In any alternating current cycle, the energy that's not being used by the power line is returned backwards through the power line back to the generator. It's a traveling wave type situation. If you don't use the electricity at the end of the cycle, it all thunders back down the power line and resyncs with the generator. So there's no energy lost in an AC system the way there is in a DC system. Well, this one's got a little game too. It goes on and then it goes off. So none of these things are useful. Okay, let's go to the next one. Okay, so this is represented by, we have two situations, one of which we call the power factor, and one is what's called the induction factor. And these are the proportionalities between the total flow of electricity. The power factor is the amount of actual electricity utilized to the total amount of electricity in the system. That ratio is called power factor, and it's represented by the cosine of the angle of how we're moving around in the deal. And our complementary one is called the induction factor, and that is the ratio of how much energy is stored in the electrical system to the total amount of electricity in the system. So basically, A plus B, in some sense, is the total electricity. Okay, let's keep going. So this, our generalized equation is any time function of alternating current, which is symbolized by gamma here. That represents a second-order differential equation. In this case, it's symbolic in the Heaviside method. Equals A plus KB. So we're using K as our most generalized operator. Instead of J, I usually use K in the more abstract forms because J may grow out of it. So we can't add A to B directly, but we have to add them at right angles, as we've seen with R and X, in a Pythagorean manner. Now this is where these conic forms come in, because we're working now where the planes, the angle of hysteresis is 0, and the planes are producing circular functions or alternating current phenomena. We haven't worked out of that yet. So let's go to the next one. And then these are our basic, Pythagorean rules and our trigonometry to figure out where the angle's at. So let's keep going. So this is our basic relationship. So if we go one step around, then this is our basic equation we use. So if I'm adding up the voltage in an electrical system and it has these phases, in other words, if that vector is on that part of the rotation of the generator going through its 360-degree cycle, that point is represented by this algebraic equation. That tells me where I am on the cycle and gives me how much electricity is being used to how much electricity is being stored. It's all inherent in this simple, basic junior high school equation. Okay, let's keep going.
Don't you need a square root there on the right-hand side?
Go back. No. That's on the right-hand side is a differential equation. That's a second-order differential. In other words, that's d squared dt squared. That's a symbol for it, but I don't want to start throwing calculus at people. So basically, we're dealing with a second-order function because we have two values, and we're in the dimensions of time because it's the number of percents of cycle going around, which is the cycle in per second, which is a time function. So the generalized function in time, which is gamma in t, in time, to the second order, okay, is equivalent to this. So instead of using a differential equation to describe this electrical situation, which is hideous and complicated and really not defined, we can do it with the Steinmetz method and just have a basic, simple algebraic addition. So I have my two, I have A on the bottom as a length, and you can see the triangle that represents it. And then I have B as the vertical, and you can see the triangle that represents that. And the quantity of the two always have to equal that unity vector. These are our basic circle functions. I don't have much time to discuss this. I have to keep flying.
So the exponent is 2, not 1/2.
Yeah, it's squared. That's not x, that's gamma. That's the Greek letter gamma in the parentheses.
Alternative to the laser
Yeah,
pointer.
there we go. Okay. Okay, so let's, I'd like to have the time to really make it so people could understand this, but right now this is all for show. Because I could make 10 lectures on this. So I'm just flying through this so people can kind of see the symbols, and the people that understand more can kind of see how this leads into more advanced mathematics that hasn't really been fully developed yet. particularly with regard to the synthesizing energy and Tesla transmission. Okay, let's keep going. Keep going. Okay, so now we've gone from there around more. So now we've multiplied the equation by another quadrant or another value k of moving around. So I've taken the relationship and multiplied it by the operator, which moved us 90 degrees around the cycle. So now we have our voltage and current type things are represented by triangles now in another quadrant. And we keep going around the cycle. Let's keep going. These are the equations that represent it. So what I've done is I've multiplied my equation by the operator k, which has taken me around now 90 degrees. So now I start to have a new relationship which explains how the electricity adds up in that quadrant. Let's go one more step. Okay, so we start to get our mathematical table. So if I square this operator, it equals -1. If I take it to the first power, obviously it equals itself. So we're starting to develop a multiplication table to use in AC analysis in the Steinmetz method. So let's keep going. Keep going. Okay, so now I've gone around one more quadrant. Okay, now let's look at its equations. Next one. Next one. Keep going. We got an equation. So now what I've done is I've operated on our basic relationship with k to the second power. In other words, now I've gone around one more. So this multiplied by this, now I've gone into the third step of rotation, and that gives us another multiplication table that k to the third power is also equal k to the 1 power, actually should be -1 power, or -1, okay, it's minus k to negative. So basically I can take all these and still turn them into a kind of plus or minus in my multiplication table. So let's go to the next. Keep going. Now we've gone one more quadrant. Okay, so now I'm starting to get another pole. So let's go to the equation. Okay. Keep going. Okay, so now we have, if the k to the fourth power equals +1 or k to the 0, so now we're starting to come back around the cycle. We're starting to sum up where we originally were. So let's go to the next step. Next step, keep going. Okay, so this is our basic relationship. As we move around the cycle, we use the interrelationships between these two quadrature quantities, this direction being symbolized by the number 1, which of course is not there because 1 times anything is 1. But then this one is prefixed by the letter k, which means no more than the thing is at right angles to 1. And the sum of these two on a Pythagorean basis gives us the actual point on the cycle, and then the quantities we're dealing with in their relationship. And this point is represented by that differential equation symbol. So that's where we are is represented by that point. In other words, that's our differential equation of motion. Okay, keep going. So these are more going through the cycle. Keep going. Keep going. I'm just not going to read it. Okay, now we're going backwards. Remember there was two. There was one cycle that went forwards and one cycle that went backwards. Just race through these. It'll be the same type of thing, except now it'll be in the denominator instead of the numerator because we're going backwards. Keep going. Keep going. So what we have here is we developed the mathematics where we're talking about an axis of rotation. So instead of using vectors or differential calculus, we're using what are called versor operators, where basically k represents an axis that we're rotating on, and every power of k, if we take k to the 0, we're at start. If we take k to the first, then we've moved 90 degrees. If we take k to the 2, we've moved 180 degrees. If we take k to the 3, we've moved 270 degrees. If we take k to the 4, we're back to 0 degrees. So basically, k is a logarithm to the base 4, but we're using a new type of logarithm now that's not like the normal logarithms they teach you in school. Okay, let's keep going. So this, well, go back. So this basically is, we have k to the base 4 as an operator. No more. It's not like an algebraic quantity. There's no quantity. The quantity is only 1. It's a unit. But we raise that to a power, and that power tells us where we are on the clock dial, basically, because they call them clock diagrams in alternating current. To draw all these diagrams is hideous through your calculations. When you can plug it in to simple plus and minus equations, addition, subtraction, then all of a sudden you can see things that before would just be too tiny on the graphs and you couldn't measure with the rulers. Okay, let's go from there. So we start to develop our multiplication tables out of this. So we get all our poles. Keep going. You went? Yeah, so these are our more generalized equations, so we can start to break it down mathematically, which we don't have time today. Keep going. So we get our definitions, which we saw earlier. Keep going. So these are our 4 poles. Okay, keep going. And then we start to develop our multiplication tables. So in a generalized sense, then we can move through these cycles over and over and over and over and over again with a more advanced type of exponent. And then develop further. Keep going. Keep going. Keep going. Go back, 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 back. So this becomes our generalized equation. These represent the 4 poles of alternating current. So if I have resistance, I have conductance, I have magnetic inductance, and I have dielectric susceptance. Each one of those voltages or currents or powers or energies will reside in one of these poles, and I have to add them through this system of complex addition and multiplication in order to calculate this stuff with general, high school mathematics and no calculus. That's what all this is about. That's what made Steinmetz famous. All the hard stuff all went away because this is just basic stuff that anybody could learn in grammar school, basically. I taught a lot of this stuff to my sister when she was in the 8th grade. Okay, or the 6th grade, I should say. Keep going. So these are our basic, as we go through the power, then we have our familiar J and -1 and +1, but we're going to go beyond that now. So we don't have time to really reside on that. But these are the values we get as we move through our poles of our 4th power, our base 4 operator. So the first power gives us -J, second power, and then multiplication and division, we keep going. So if we divide, this represents 1 over k squared, and that also equals k squared. So we start to get an interesting relationship where a quantity divided into 1 equals the same quantity multiplied by 1. Keep going. So we just worked through all this, a forward and reverse rotation. Keep going. And then some more, representations of this is what the mathematics people need. So you define your terms. Keep going. Then this can be expressed also trigonometrically, which is the very thing we're trying to avoid because then we have to use sines and cosines tables. Keep going. We can get into, these are all trigonometric. This is the way this stuff is normally dealt with, which is way too complicated in your trigonometry they teach you in high school. Then we can resolve these things into infinite series in order to get the numbers without the tables. This is all basic trigonometry raised to the base e's. These are all your normal processes you go through to define your mathematical relationships and take them back to the definitions of the terms, which are all based on what are called infinite series. Okay, now we're going to expand this out. Okay, now what happens is when I was talking about this cylinder, which had variations in it with respect to time, these are Steinmetz's curves that he made on machines that were starting to produce energy anomalies. And what we have here is a situation where there's a wave in the wave, or what you would call a canonic wave, like in music, where one melody, but then another melody will start later in another time, but the harmonies will match up by some strange formulation that the musician has to create, so you can have 2 of the same pieces of music occur at a different time, but still be one music. The wave in a wave type situation. So Steinmetz found that the sine waves went away and started producing these asymmetrical energy exchanges, and the law of conservation of energy started to break down. So normally, this would represent the pressure, temperature, volume situations in a cylinder. And for air compressor, let's say, where there's no combustion or energy being delivered into it. But this would be the curve if now we took the air compressor and converted it into a gasoline engine, where we still have the valves and cylinders, but instead of putting air in, we put diesel in, let's say. And now it's a combustion cycle. As it goes through the cycle, okay, instead of the normal progression, we're dealing with this exchange. In other words, cause and effect are no longer happening at the same time. In this situation, the cause comes first, the effect comes later. In this situation, and we can get away with this in alternating current, first we have the effect and then we have the cause, and this is called the hysteresis loop. This angle of hysteresis, okay, where this thing is actually a circle and it's rotating. These are distorted waves produced by real machines, but this ideally would be a circle, If the circle turned sideways, it would be a straight line. There would be a direct proportionality between cause and effect. But as we start to take that circle and move it, like that plane on the cones, we start to get out of that dimensionality, okay, and it opens up into this ellipse. And then the ellipse keeps turning, and then it turns into a circle. And in that situation, cause and effect are non-related. At the point they can't really be corresponding anymore, and they start to lose sight of each other. It's a very complicated thing to explain, but it's produced by this fact that the inductance and capacitance, like we showed earlier mathematically, when they vary with respect to time, then we end up with resistance and conductance, which means energy is either appearing or disappearing in the system from another system of dimensions, or it's being dimensionally taken apart. And these distorted waves then produce these energy imbalances because there's not the same amount here as there is here anymore. It's not balancing out. Now this requires another type of mathematics, more advanced symbolically, which we'll just briefly go over. But this is the way in which you synthesize energy, is you start with this method in an alternating current system. And this is how these power systems would take off on their own, is by developing these hysteresis cycles of these big arcs, changing their properties with those AC cycles, and causing the cycles to distort in these fashions, and then all of a sudden the energy balance goes off into some way where the energy is basically being built out of pieces, out of time and space and induction. And the various things that make energy are being synthesized by delaying the cause and effect reactions or advancing them and separating from each other. It's very theoretical and hard to explain, but this basically is how this stuff works. This is if you're going to do it in an engine, if you're going to do it in a motor, if you're going to do it in a static electrical system with coils and capacitors, it has to be done in this fashion. This is basically how you synthesize energy. Okay, go back. So this is like going from power consumption to a point of power balance, and then our energy consumption, and then into energy creation. So this is where these machines will either consume energy or they will produce energy, and the law of conservation of energy has to be redefined in this situation because it appears to be that energy is either vanishing or being created, which requires a new way of trying to describe this to keep it into what Heaviside called the law of continuity of energy. Okay, let's keep going. So we basically have to develop a more complex type of mathematical operator. So this basically is the operator we've been using all along, is we have a type of logarithm to a base raised to a power, which is symbolized by 1 to the 1 over nth power. N being how many poles do you want to describe in your electrical system, whether it be 4 or 8 or 16 or 32. But conventional mathematics will only work with the even numbers, unfortunately. If you try to use odd numbers, like in three-phase or any of that type of stuff, then all of a sudden all trigonometry fails and a new type of math and a new type of logarithm has to be developed. This is something I haven't finished yet. So we get back into our basic, let's just keep, we have to skip over most of this. These are our basic expressions we use, which now we're trying to advance out in a more generalized form. Let's keep going. So we're expressing, go back. So we're expressing now, we have frequencies where we're no longer going to express these frequencies simply circular, a real frequency in cycles per second anymore, but now we're dealing with these spirals and impulses. So now we have to have another type of frequency, which is called an imaginary frequency. And we use our operator, again, our so-called imaginary operator, to combine these two frequencies. So now instead of having, we have a complex frequency now. Instead of cycles per second, the frequency is expressed in decibel cycles per second, or in trigonometric terms as Nieper radians per second. Because in mathematical calculations, it's always radians per second and not cycles, because that way it works out in the exponential equations. And this is called Niepers. So if I have a 1 farad capacitor and I discharge it into a 1 ohm resistor, in 1 second, the amount of energy in the capacitor will drop to 1 Nieper lower than it was originally. So what it is a non-cyclic variation in time, where radians are a cyclic variation in time. And the composite of these is what produces the 8 waveforms we've seen, because this one can equal 0, or that one equals 0, or they can combine in the same way that we were combining the reactances and resistances, now we can actually work the frequencies. So we're starting to develop now more complex differential equations in order to penetrate these extremely difficult electrical situations, which I just showed you, which are basically unexplainable. Okay, let's keep going. So we're getting into our power relations. Let's just keep going and we get to the final deal here, because this is, okay, so this basically is an alternating electric wave. This is one half of the sine wave, and this is a aperiodic electrical impulse. So this wave is moving in radians per second endlessly. This wave is moving in meters per second and tends to go on indefinitely also, but it doesn't cycle. It just keeps getting a half of a half, a half of a half until there's nothing left. So this is called an alternating electric wave, and this is called an impulsive electric wave. So these are the waves that Tesla was using in his research. And they produce a different type of effect. Okay, but now the important thing is, go back. The important thing is the peak of the impulse is exactly 1/8 of a cycle behind the peak of the sine wave, which shows us our 8-pole relationship that I was going back to in the beginning. So basically, normally in the Steinmetz method, you have one operator for every quadrant of motion. But now, in order to explain these more complicated names, we have to have one operator for every half quadrant, or 45 degrees of motion. That's why we use 1 to the 1/8 power instead of the Steinmetz method of using 1 to the 1/4 power, because we're trying to develop the mathematics for a more generalized electrical condition. Okay, keep going. Then finally, to develop these canonic waves, I'll just go to the end of this. Keep going. Keep going. This is all the proofs. We're not here to prove anything really right now. I just want to get to the last page. Okay, so now what we have is we have an operator to the operator power. That is the way in which we can describe these hysteresis situations or these distorted electric waves where the energy now is no longer balanced. So we have what's basically called a primary quadrantal versor operator, which is here, but we raise that to a secondary quadrantal versor operator, which is here. So we're taking basically the square root of -1 and raising it to the square root of -1 power. And when we do this, then we can start to see these electrical waves flowing in the system the same way that Steinmetz did when he developed the light second as a way to measure power lines. So if you had a 100-mile long power line, then you measure that line. It's going to be a fraction, but that's why you have powers of 10. You measure the length of that line and how far light goes in 1 second. So if the light goes that far in 1 microsecond, then that's 1/millionth of a light second, and your power line is 1/millionth of a light second long. But you use your powers of 10, then you don't have to worry about the decimals, and you can still calculate it. So it doesn't matter if it's very short with respect to light. You might say it'd be better to use the light microsecond. And when Steinmetz did this, he found there was a whole other class of waves flowing in the power line that was exchanging energy between the various sections of the power lines and the transformers, and that's where these transients were coming from. Is one power line was dumping its energy into another power line, which then was dumping its energy in another power line. When the waves came through the system, some power lines would deliver energy, but other sections of power lines would absorb energy, and then the transformers would deliver more energy, and it produced these very complex waveforms that up until Steinmetz's time there was no theoretical explanation for. But when the Manhattan Railway project or railway disaster occurred, then it had to be analyzed. They didn't want to play with this anymore. There had been too many fires and explosions, and the public was not interested in playing games with this stuff anymore. So Steinmetz spent 2 years and wrote about a 600 and some odd page book developing these concepts, but he never carried it into the symbolic operators. He just didn't have the time to do it, and he died fairly young, I think at the age of around 50. Okay, let's keep going. Okay, now what's never been developed as a mathematics of symbolic form for space, and Heaviside and Steinmetz all felt it was impossible because algebra is basically a mathematics of time. When you try to take algebra into space, it's normally done with the Maxwell-Heaviside equations, which are really useless for electrical engineering purposes. So we have to, in order to describe Tesla's electricity, which basically moves at right angles to conventional electricity, We have to come up with a system of space operators that work in a fashion in the way that the time operators did. And as far as I know, I'm the only one that's ever been able to figure this out by working out of the pieces of the people that carried it almost all the way and then died or lost interest or whatever happened. It's just somehow there was the mind blocks in these early people. They could take it so far, but they just couldn't see the final step. Like in Steinmetz's case, he was harassed by Pupin and all the rest of them to take the minus sign out of his inductance equations and replace it with a positive. In the process, it folded the two waves over each other, and it wouldn't convert to energy, and you had to use non-algebraic means to do it. It was that simple. It was just the minus sign and the plus sign being interchanged, and that was enough. But the mind block was there, but you only can take it so far. All of these people could only take it so far, but the experimenters like Tesla and Thomson were less interested in that, and they just fooled around and used their ideas and created things that worked, but it took Steinmetz and Heaviside to say why it worked and how to calculate it. That was not Tesla's world. Tesla just envisioned the stuff and could build it out of his head. Without Steinmetz, we would have no Tesla. So let's keep going. We'll show this graphically. This basically is our generalized flow of electricity. In this case, a more general transmission structure where the power line only has 2 wires. This represents the inside of a transformer coil, which has thousands of wires. As soon as you get into that situation, the electrical field becomes so complex that no one has ever been able to solve it because no one's been ever able to develop a symbolic algebra for it. This is the symbolic algebra. Let's keep going. So we take that element and we put them in tandem. This represents a transformer winding, where this is the wire at the phase lead and this is the wire at the neutral lead. Yes, this is how energy flows in the transformer. You can see it's a very complex relationship. Now it's not just a simple A plus JB. Now we have what are called 2 degrees of freedom or propagation instead of 1. And that gives us a 4th order differential equation, which normally can't be described in a spatial reality. But as we saw in the beginning, we had centimeters to the 4th power. Obviously, those dimensions do exist. There is a 4-dimensional, in physics terms, type of spatial relationship in electricity rather than 3-dimensional. It's not 4-dimensional in space-time, it's 4-dimensional in space. In physics terms of dimensions. In my terms, it's only 1 dimension, it's in space. We express it as 1 dimension in space because we're using the number 1 to describe all of our process. So let's keep going. So basically, if we take 2 windings on the transformer, we take 2 turns. The stuff's usually wound with square material so that the space in between is not left void for leakage magnetisms and stuff to swirl around in. So basically, it's bars of copper. So we have a planes here. So we use our same type of mathematics that we use in alternating current. In this case, this is an electromagnetic wave. So the energy is like flowing down the 2 wires, and these are our basic magnetic forces type of situation. So this vector would represent electromagnetic flow, but we have another vector now which represents a different type of flow. We have 2 magnetic fields. We have the magnetic field that's trapped between the wires in the earlier diagrams, but now we have another magnetic field that surrounds the wires. So we have 2 magnetic energy storages, and in space they resolve into a situation where there is a net resultant magnetic force. But it might, like with the alternating current, it might not necessarily be representable as a plane figure, but we're using that now just as a calculating model. So let's go on to the next one. Keep going. Keep going until we get another picture. Okay, now this is the electrostatic field rather than the magnetic field. So now we have the electrostatic field whose radial lines stand between the conducting materials. And then we have the one, this would be the one of attraction, but this would be like the one of repulsion, where the lines are going out to other conductors in the system. So now we have 2 electrostatic fields and 2 forms of energy storage, and we have a resultant in space of the direction of this field. Okay, let's keep going. So we're starting to explain this now. This was Q, our total electrification, okay, which we know is a product of 2 inductions. So let's keep going with that and see how we can apply that to space. Okay, so we've gone through all this. We know these relationships. Okay, so we can represent one of them one quantity as the electromagnetic quantity, which would be the sine of that angle. Let's keep going. Okay, so we have like an axis here. Okay, and we have the dielectric field and the magnetic field, and these are where the two lines cross, as we've seen in the circle diagrams around the conductors. We've blown this up now into an elemental space, which is so small that the lines appear straight. And these are the actual lines themselves, the little ether particles all lined up. Where these cross, in terms of quantum physics, these are what are called photons, okay? And they have specific sizes, and they represent Q, the quantity of electricity dimensionally. So these photons are the electricity, and they're basically, in physics, they're energy multiplied by time. They're not energy. And we saw that if we take the rate of change of the electrification Q, this growth or decay, that represents the energy. So energy can go back to or come out of the electrification without defying the law of conservation or law of continuity of energy. It may defy the law of conservation of energy, but not the law of continuity of energy. So we're expressing these things the same way we did with the other operators, but now we're in space, we're stuck to a different set of constraints. Okay, keep going. So we're going to define these as our basis axes, okay, where we have one axis, and then we use an operator to define the other, not the axes, but the directions, and these are revolving around the axes. So we're trying to utilize this process. There's no way I can really explain it. I'm just showing this all is a demonstration. So each one of these things, we're talking about 10 or 15 talks in here. But I'm just trying to give an overview of electrical theory and science and how it moves. Okay, let's keep going. So again, we're familiar with how this process works. So we have a quantity of electricity Q. This means that it has a direction in space. So we have one quantity, which we'll call the non-electromagnetic quantity, or the Tesla quantity. And then we have the other quantity, which we'll call the electromagnetic quantity, or which is called the Poynting vector, after another scientist whose name was Poynting. Good name if you're into vectors. So keep going. Okay, now energy by physicists is described as mass times velocity squared. Okay, but we don't have mass in electrical equations, but in order to go into physics, then we'll use this as our reference point to bring it to an area where people with physics knowledge can maneuver into these equations using their systems of dimensions rather than electrical engineers' systems of dimensions. So basically, if I have a magnetic field, okay, the electric current associated with that magnetic field of magnetomotive force, in other words, the magnetomotive force producing or related to the magnetic field, if I take that and compare it to the amount of energy in the system, then I have this basic simple, like the pressure, temperature, volume relationship that gives me the relations between magnetic force, magnetic induction, and energy. And then we can start to develop other types of relationships to maneuver in these things to get our dimensions, but this is beyond the scope of the talk right now. So we have, again, these are basic things. We know that we vary the dielectric with respect to time. That gives us the magnetomotive force. These are our normal energy relationships, so we can continue to maneuver around. Let's keep going. Okay, now what it is the Planck is a integral value quantity because the lines of force have definite dimensions. So every two lines of force that cross to produce a photon, being that the lines have size and a finite relationship where they cross, I believe it was found out by Max Planck, I believe, that the amount of flux density can only increase in unit steps, and these are the size of the steps. This basically gives us the size of the electric and magnetic and dielectric lines of force, and the photons exist in these discrete units because we're dealing with discrete lines of electric force. It's not a continuous medium. These lines of force actually exist as space-definite quantities. In other words, it's here, but it's not here. Okay, so these are more the trigonometric relations. So in Tesla technology, the magnetic lines of force and the dielectric lines of force work in space conjunction. In other words, there are no right angle relationships and there's no photons. It is non-electromagnetic, therefore there is no velocity. Okay, let's keep going. So this is how we maneuver around. It's beyond us right now. I just want to get to the opposite relationship. Oh, go back. That was right. Go back. Go back. Okay, so this would be, so I don't know now. I might have missed something here. It doesn't work. We lost a few pictures, so. At any rate, if we have these lines at all right angles to each other, then that's our standard electromagnetic wave. In other words, if the magnetic lines and the dielectric lines and the movement of the photons or electromagnetism are all in quadrature to each other, that is our standard electromagnetic wave, like the one that flows down the power line. But the other one of conjunct waves is more of the type that flows through the windings of the transformers, because there has to be two types of flows in the transformers, the ones that go in between the windings and the ones that go across the windings. And the total flow of the transformer has to be the complex addition through Versor operator of the two. Then we get the total electrification. Now, physics tells us that the other component doesn't exist. That's why there was the explosion at the shipyard. Okay, let's keep going. So this is the movement inside the transformer. This is the primary winding, okay, which we'll say is 12,000 volts, and this is the secondary winding, which is 120 volts. So the metal is broken up fine on one side and coarse on the other. In this case, it would be 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2. So it's a 4-to-1 transformer. So this would be a 440 to 110 volt transformer. So we have the flow of electrons, which represent the resistance, dragging along with the wave, heating up. Then we have the flow of energy, okay, which normally goes between the wires, which is electromagnetic. Okay, so the electron flux moves along with the energy flux of electromagnetism, but we also have mutual induction and mutual capacity that carries energy from this system of conductors to this system of conductors, and those lines of force are all conjunct. So the Tesla energy flux flows this way from primary to secondary, and the electromagnetic flux flows this way in between the wires. In a transformer, the electromagnetic flux is parasitic and represents useless energy flow, and you do everything you can to eliminate it. You strictly want what's called the mutual flux. You don't want the self-flux. This is what Tesla worked with in his transformers. Let's keep going. These are again, our Versor operators. So this is our, go back to the circle. So this is our basic movement through the cycles so that we can get the net sum, just like we did in alternating current, how much Tesla waves and how much electromagnetic waves result in the total electric flow in the system. Keep going. So these are moving through all our various formations, which is beyond the scope of the talk right now. So this represents the dielectric equation. The other one represents the magnetic equation, which are oppositely directed. And this, go back to the other one you just had.
Oh, this one.
Yeah. So this is the entire situation. So we have the electromagnetic waves. We have ones that rotate, what you might call vertically polarized. You have another one which is horizontally polarized. Then you have the Tesla waves, which move at right angles to that, which have no polarization because they're longitudinal. And then you have a scalar product, which cannot be defined in the dimension that takes it out of it, like the weighted point in the resistance-reactance diagram. So basically, I just symbolize it as an expansive or contractive, or what you might say a non-zero divergence of energy in the system. So this would be where energy would come out or energy would go away. But this is still very experimental. This is like Heaviside's math. So it's subject to criticism and subject to experiment and further work, but this is the basis in which to develop this on.
When you talk about energy coming out or going in, is it kind of like a sphere moving through a plane? If you think of the sphere as the energy?
No, it's not like that at all.
Okay.
Let's keep going. Okay, so these are all our multiplication tables. Keep going. So we're going to get more into the practical stuff now. Let's keep going. So these are our we call this circularly polarized electromagnetic waves. One is clockwise polarization, the other one's counterclockwise polarization. Keep going. These are all longitudinal waves. Okay, these are longitudinal wave going one way or a longitudinal wave going the other way. And then we have our scalars. Don't go away so fast. We have our scalars. So we can represent this as we have a piece of rebar stretched between here and the door, and I hit the rebar sideways, transversely. It will produce waves, transverse waves, like electromagnetic waves, which will move at right angles to the direction of energy flow. That's the electromagnetic wave. But if I take the rebar and I hit it this way, the wave ends up there almost instantaneously, and you can't see anything move. That's the Tesla wave. These are the two types of waves we're dealing with, and this is the mathematics for describing it using the Steinmetz method. Okay, keep going. So back to tables, we don't need those. Let's just keep going. I think we're done. We're done. Okay, yeah, it's just how the transformer windings look. Let's keep going. That's more multiplication tables. Okay, and these are special cases. All this is very important, but I don't have time for it. We're already at 5 o'clock. Keep going. Okay.
You can go longer.
Okay, let's see how long everyone wants to put up with it. Okay, now this is the workings inside the transformer windings. Okay, let's go ahead to the transformer. I think it's up ahead here a ways, isn't it? No, it'd be too difficult. Go back. As soon as I hear I know we can't. Okay, go back. Go back, all the way back. Okay, so,
Oops.
no, just diagrams. Okay, so if I take 3 windings out of the thousands that are in the transformers, okay, there's flux lines. Okay, in this case, as we know, the magnetism surrounds the metal, and the dielectricity terminates on the metal's molecular dimensions in between. These cross at right angles in this case. So we can represent this as a basic electromagnetic condition, which represents the flow of energy at right angles to these lines into or out of the paper. That's the electromagnetic power flow in the transformer. Let's go to the next one. Okay, this is the actual lining up of the flux lines. This is how they actually look in space to a certain degree. And where they cross, that creates the photon flux, which represents the energy flux moving down the space between the wires. Let's keep going. That's basically how it moves. Okay, keep going. So what we're looking at here is this is the windings of the transformer, okay? And we're looking at these 3 turns. So we're starting to work into this is a Tesla coil, let's say. These are the dynamics inside the Tesla coil, which is not operating as a normal transformer because it's compounding these waves now instead of just isolating out specific ones. Okay, I came up with the engineering math in order to calculate this for any simple solenoid to make it operate in the Tesla mode. These are not abstract. These are basic formulas for people to sit down and measure the length of the coil in inches and find out the frequency and impedance. We'll just run through all these real quick. Okay, now this is the longitudinal wave. Okay, now the mutual magnetism surrounding the windings, okay, and the dielectric flux between the windings is now moving in the same direction. This is how we're starting to get the Tesla wave rather than the electromagnetic wave. Keep going. So now our flux patterns are combining. Let's keep going. I think we've got them all backwards here. One more. Okay, one picture is not in here. Go back, go back. So I have to take my word for it. Keep going back.
Back.
Keep going back. We always want pictures. We don't want anything else other than pictures. Okay, yeah, we got the flux lines. Okay, so go to the next one. We got them all. So the basic energy now is not in photons, but is in these longitudinal forces moving between the 2 conductors in a direction carrying from one conductor to the other, where the electromagnetism is at 90 degrees displaced. In other words, one Versor rotation in the other direction. So we have our 2 Versor components, hence the A plus JB. Reality can still be applied to this, but in a somewhat more complicated fashion for space, because we're dealing more with multiplication than we are addition. Okay, keep going. So the energy now can't be blocked by metal, so to speak, anymore. And these longitudinal waves, that's what carries the energy from the primary to the secondary of the transformer, even though the physicists say these waves don't exist. If you do it the way the physicist says, you have the explosion at the shipyard. Okay, let's keep going. These are all the formula for making your own Tesla coils. We don't need any of that. Keep going. So this is basically how the resultant energy moves around the Tesla coil. Okay, we have energy flow A, and we have energy flow B multiplied by operator K that says we've gone from longitudinal to transverse. And if we take our resultant, then that means that the flow of power around the coil will spiral, and therefore the velocity of light will no longer give us the right results because we're no longer flowing in between the wires, but now we have a composite flow. So that way, it appears that the velocity of light is being exceeded in designing the system. Even Tesla wasn't fully hip to this because he had so much goop around his coils. It pulled the frequency down and it made it appear But in his Colorado Spring notes, you finally see that he was getting frequencies of oscillation higher than what you would calculate by saying the energy moves around the coil at the velocity of light. But he never mentioned it, but it's in his equation. These are all standard formulas. Standard formulas. Standard formulas. Okay, keep going. So this is the actual transformer winding. So we can see all these little squares in here. Now substation transformers are wound with stacks of pancake or Tesla coils to minimize the voltage gradients and to keep the mutual induction going. So each one of these is what's called a pancake coil, and they're stacked in series. Okay, now the first attempt to analyze these waves in Steinmetz's time resulted in complete blockage because the differential equations were too difficult to solve. And as Steinmetz said just before the explosion at the shipyard, that the Maxwell model does not give us the combination of transverse and longitudinal fluxes, but nets them into one. Okay, now the guy that wrote this book, Bewley, I was lucky to get this in high school, but this was my first exposure to the differential equations and the idea of non-electromagnetic waves, but he didn't get it worked out because he went from Steinmetz back to Maxwell and Heaviside, but nevertheless you get your first taste of the math. Okay, let's keep going. Keep going. So these are our various things we were talking about. We keep going. This is his model of the inside of the transformer, which is not correct, but it starts to develop the theory. Keep going. So these are all the forces and all the geometrics and the dimensions of our thing, and we keep going, and we finally develop into our differential equation. Okay, so this differential equation tells us again, we have, in physics term, we have 4 dimensions of space. Okay, the problem is using the Maxwellian term, this term centimeters cubed, or 1 centimeters to the -3rd, because it's in the denominator, keeps appearing in the equations. This is the missing element that splits the magnetic fields. And we'll get into this a little later. Let's keep going. So how would you like to solve that? I think my stuff's a little simpler, don't you? But this is how you start to really get the physics of the matter down. Okay, keep going. So these are his talk about it, but this is kind of, so now I've come up with this is basically, we're using the Alexanderson antenna Bolinas now as our model to develop the dimensions of this type of energy flow, because it had longitudinal as well as transverse wave propagation, which were phased in such a manner that there was no velocity of propagation whatsoever. It was infinite, or undefined. So the entire antenna, even though it was 3,000 feet long, the voltage was in the same phase at one end or the other, so the whole antenna would move in unison instead of Marconi's, where the energy had to go back and forth and didn't engage in the radio wave, but just had all this bouncy that caused heavy voltages and currents that did nothing. Alexanderson eliminated the electromagnetic wave and kept the longitudinal because you wanted to transmit out into space, not from end to end of the antenna. It's a very significant invention, and the implications are stunning. Okay, keep going. We want to go to the math. Okay, so we're going to take this circuit representation as an analog computer to do calculations on. This circuit represents transverse electromagnetic power flow, where the lines of force are at right angles to the flow of power. This is the inductance of the space between the wires. This is the capacitance of the space between the wires. These are 2 wires like the ones we showed on the telephone pole. Okay, let's keep going. Now we have an inverse relationship. This is a longitudinal or a Tesla type of wave. This is like between the transformer. We have the mutual magnetism between the 2 windings, primary and secondary, and the mutual capacity between the 2 windings. And now the energy is being carried where this way would be the electromagnetic. Go back to the previous one. Okay? See the same physical relationship. Okay, now go back to the next one. It's the same thing but turned 90 degrees. This is where the versor operators come in. These are the same coils and capacitors. This is an analog computer that I built. Charles saw these down in the desert. This is how I do my calculations with analog computers, because they're real. I can put a voltmeter on it and I can get shocked off of it. Okay, keep going. So now we're combining these things into what I call concatenated, where one network is compounded into another network of a different form, and we're taking the longitudinal and transverse and mixing them together. What's going off on us now?
It's
Flickering
conspiring.
a little bit.
The machine, the computer goes together.
Okay.
Fine. Next.
Okay, let's keep going. Okay, now this one here represents the power flow in a Tesla coil. We call this a shunt concatenated transmission network. Okay, keep going. Now this represents the system of the Bolinas transmitting antenna, where part of that was compensated out by the opposite network. In other words, the transverse and longitudinal were phased with each other to cancel each other out. This is how the antenna in Bolinas was connected. Okay, keep going. So this is our test setup. Here's our experimental network, which consists of 10 of these circuit elements hooked in series to make a transmission line or a transformer coil. Each one of these previous diagrams you saw was like one turn or one pair of wires, and then we connect them together to get our total line. So that's represented by this box where Z represents the impedance and Y represents the admittance, which we went back to earlier, which is our basic ratios of magnetism to dielectricity. And the product of those two gives us our speed of propagation or our velocities or time lag or whatever differential function we're dealing with. In other words, what dimension are we changing in? Are we changing in space? Are we changing in time? This gives us that factor. This gives us that gamma to the base and to the power that we saw earlier in the AC equations. Okay, let's keep going. Okay, now this is the response of the networks. Is there any way we can stop this thing from flashing at us? Or is it, like everything else, is it digitally out of control?
Pretty much.
So color wavelength is out of phase.
So that's why I really encourage the complete dumping of all of this digital technology.
Like I said, the machine's conspiring. That's the whole explanation right there.
They know you're an analogic.
As I walk away.
No, it's nano. It's what's called nano-nemesis. It's built into all digital technology. It's deliberate. It's a Trojan horse.
Try the laser pointer again, third time's luck on that.
Well, I guess we have to live with it. No, if you push any more buttons, it's over, George. It's tempting us to do that, okay? So let Lenny play with this. We'll just hate her for it. Okay. So we start to measure the bandwidths of these networks. We find that the normal transverse network, like a telephone line, okay, has what's called a low-pass condition. In other words, if we increase the frequency, we get to a certain point where the line will no longer pass the frequencies. It will only go so far, and then it will cut off. But in the transformer or longitudinal type waves, it's the other way around. Okay, if the frequency is low, it cuts off. But as the frequency raises, then it comes up to the ability where it can operate. So we have two complementary types of waves. We have one which we call high pass. In other words, the highs are passed and the lows are cut. And we have one that's low pass where the lows go through and the highs are cut. This is standard electronics technician terminology. Okay, let's go to the next one. Okay, now we find that these things generate harmonics, but now the harmonics are not simple multiples anymore, but are complex. These networks develop harmonics that are distorted so that we have a complex type of situation, more like musical chords rather than just simple harmonics. So this network here is, none of these are in order, everything's all mixed up, which is just making it hell. But this represents a complicated harmonic pattern of one of the networks. This one is the longitudinal network. So our harmonics basically are backwards in this case. Let's go to a forward one because I can't explain something without. Okay, this is our normal harmonic deal. Okay, so we have the fundamental, and then we have the next harmonic above that, and the next harmonic above that, which are progressively weaker and higher in frequency. This is a standard overtone series for any type of dynamics, like a guitar string or any of those type of things is explained in this harmonic situation. Okay, let's keep going. We'll go back. Let's go back. Go back. Go back. Now go back. Go back. Now in the longitudinal one, the harmonics are backwards. So instead of the third harmonic being 3 times the frequency, the third harmonic is 1/3 the frequency. Now this is something completely unprecedented in electrical network theory. is a backwards harmonic slope. Okay, keep going, forward again. So those are our two harmonics. So this basically then, now we're starting to, this is our bandpass flows. So let's just go beyond all this. I just wanted to show the two harmonics. Keep going. Okay, now this is the oscillatory discharge of these waves in a Tesla coil configuration, which is basically the frequency becomes slower as the energy exchange continues. Unlike the simple coil and capacitor where we're locked into a certain frequency, now what happens is we have a chirp instead of a whistle. The frequency goes down as the energy goes down. These are the type of signals you find bouncing around inside the Earth if you have the antennas to pick them up. Okay, keep going. Now this is the Alexanderson network antenna in Bolinas on an analog basis. The energy readjustment is very complex here and fights itself. So it's much more difficult to tune these type of networks than it is the Tesla network, which tends to want to become more cyclic. So you can see the waves are fighting, but it's the same thing. The frequency is tending to go down. As we see, as we measure the time between the crests and troughs, they get progressively longer and longer. This was drawn off of an oscilloscope. Both of these were drawn off an oscilloscope. Okay, go ahead. So these are the bandpass characteristics of the various networks. So we can see we have frequency complications here. We don't have just like one frequency or harmonics. We have all these various frequency relationships like sidebands. And there's a certain type of bandpass condition here where the network becomes completely transparent or scalar, and that would be the point in which you would have no propagation velocity, but it would be uniform. But it's very difficult to achieve that balance, and it's kind of beyond the scope of the discussion now. Okay, now this is another spectral plot of one of these networks in oscillation. So you can see now the harmonics, and then we'll make these things very well suited for musical instruments because now you can produce these complex tones. Okay, keep going. I'm not ready for anything yet. Please don't disturb me. Okay, keep going. Keep going. Okay, so we're using this now as our most generalized network. This is our analog computer. This represents one element, or 1 centimeter of length down the Alexanderson antenna. Okay, keep going. So this gives us the capacitance, okay, in farads per centimeter, but now we have a longitudinal component, which is the inverse capacitance, or per farads per centimeter. Okay, now we have our normal inductance L, okay, which is in henries per centimeter down the line, but now we have a new dimensional relationship, which is the mutual induction, like between the transformer windings, in per Henry per centimeter down the line. So now we have two inductions in a spatial relationship, and we have two inductions in a counterspatial relationship. We no longer have a simple double energy transient like the car coming to a stop and reversing. Now we can take the situation where not only the car moves forwards and backwards, but if you push down on it, the springs absorb the energy and push the car back up. So now we have the car bouncing this way, and we have the car bouncing this way. So now we have a complex energy interchange between 4 poles, rather than 2 poles, of energy coefficients, and it results in a mathematical situation that can't be calculated except by using the Steinmetz. Okay, so these are the standard dimensional representations that are used by electrical engineering. So capacitance is given farads per centimeter, is given in these dimensions. In other words, I have time squared in the numerator and I got length cubed in the denominator. So the capacitance in farads per centimeter is seconds squareds per centimeter cubed. These are the established by the British Association, and thereafter the dimensions that we call capacitance. Okay, it's inverse, okay, where this is considered the compliance of the electric field. This is considered the elasticity of the electrical field, which is the inverse of capacitance, the mutual or the Tesla component. In this case, if I take it on a per centimeter basis, it gives me centimeters per second squared. So the distributed mutual capacitance, so to speak, is in centimeters per second squared. The transverse or electromagnetic is in seconds squared. It's basic, simple, and same thing with inductance. Henries per centimeter is centimeters. And the mutual inductance, remember we saw this in the Bewley equations, is 1 over centimeters cubed. This is the missing link. This is what took me 20 years to figure out. This is the missing link, and it's per centimeters cubed. Now let's turn these into space-time waves. Right now our topic is space-time. Okay, this is a little clearer representation here. Okay, keep going. So now we start to combine these things to develop our differential relationships, which is beyond our talk. Okay, and this is kind of how they look. We can't get into this right now. Okay, keep going. We're arriving at something here. Okay, so now, go back. So this gives us two waves now. If we take our standard electromagnetic wave, LC, which we've seen in the past in this presentation, okay, that gives us time squared divided by length squared, or second squared per centimeter squared, which equals 1 over velocity squared, which is 1 over the speed of light squared. So the conjugate relationship, or the denial duality of these two fields, produces this velocity of light ratio. So whatever the velocity of light does in this place, this inductance and capacitance of the ether will sum up into that relationship and basically give us the inverse of velocity. In other words, we have miles. We have, instead of miles per hour, we have hours per mile. We just turned it upside down because that's the way it works out. Okay, but now we have the Tesla component, the mutual inductance and the mutual capacity. Okay, now we have a velocity in counter space. So now the dimensions of length are connected to the dimensions of time as a product, which of course can't be. So basically, our length now is counter space. So what we have, where the speed of light was upside down, we're also upside down in this, but that's just the way that the equations work. You can't get around it. So now we have a wave that flows in space on a centimeter basis, and we have a wave that flows in counter space on a per centimeter basis. So these are our two waves. This is our electromagnetic wave, and this is our Tesla wave, and this is the dimensional expression of these. We call this a velocity and a counter velocity. And the sum of them two will annihilate the velocity and give you a situation that has space scalar and there's no variation, infinite velocity. Actually, the power companies use this. I don't have time to get into the details. Okay, let's keep going. Now we also have a different type of wave where this is the distribution of the two electrostatic fields. There's no time variation because their energy is in the same type. So basically, it just varies on a per centimeter basis that goes down the line. It's a curve that just gets weaker and weaker and weaker, or stronger and stronger and stronger. And it's the same thing with the magnetic. So basically, if we abolish the Heaviside Maxwell concept completely and go to the J.J. Thomson concept, and Steinmetz came to a similar conclusion, there is no electromagnetic waves, and there aren't any of these other waves. What it is you have an electrostatic field propagating down the line. You have a magnetic field propagating down the line, and it's only the apparent superposition of them that gives you the velocity. That's why you can't see the stars or the sun in outer space, okay? Because the fields are not co-joined. The reason why the wire exists in the electrical system is so the magnetic field can exchange itself with the dielectric field. It's there strictly as a translational type of item. It's not there to conduct the electricity. It's there to translate the electricity. Okay, let's keep going. So then we have our Heaviside relationships and frequencies, and I think we've gone beyond all this now. If anybody's got the steam, we can go one more step or we can close it here because the important mathematical concepts, but I have a more a readable explanation. I think really we should cut it off at this point.
Okay.
So this is the point I wanted to get at.
Is the surface of the wire the interface to the ether, and that's actually what propagates this motion, these different forces? Is that what's going on?
Right. What Maxwell's discovery was is the electricity flows in the insulators, not the conductors.
So a person could design a chip. Just hear me out for a second.
Well, the problem is...
Hold on. Right. A person could design a chip, theoretically, with an extremely high surface area to volume ratio, many layers of like nano-thin coils.
Right.
To maximize this interface. Would that be a workable way to look at your model?
Well, the thing is, if you bring them close together, then you're storing more energy in the dielectric than you are the magnetic. But the ratio of the two always has to equal 1 over the speed of light squared if you're doing the transverse waves, so ultimately you might not accomplish anything that
Where
way.
where I was going with this
Okay.
was to make a superconductive, or something that appears to be a ultraconductive item, that instead of being a wire or a square would be a bunch of foils in parallel.
Right, well,
very,
that
very
would
thin
be
foils.
ultra-reflective.
So-
When you say superconductor, that means it's a perfect obstructor. The electricity can't get through the metal in its transverse form.
Making a nanoscale perfect surface is no longer a manufacturing problem. It's
Right.
made up. So that's why I was offering the flat.
Yeah. Well, if you form that into the shape of a transformer winding, where you have divisions in 2 axes, in other words, rather than one, you have divisions in 2 axes or 3 axes, then you can start to move these complex waves through the system. But that's basically, you're just building a transformer of very tiny dimensions.
Well, or you can build a replicatable structure on a larger scale.
Yeah.
And if you were to approach a manufacturer of this kind of thing that has this capacity, you might approach them with that idea. Well, patterns then.
Yeah, and that's kind of out of my area. Unfortunately, I didn't have time to get into the last part of this. It shows how I use this to receive these waves out of other dimensions, so to speak.
You just have to come back again
Yeah.
next month.
Well, I was trying to give you like a practical sense of like how like a big company might say, gee, we could use this for something. That might be really
Well, it's the power industry. The power industry already does this, okay? Here's the basic problem. This is where I'll close it because I got to take a break and drink some juice and maybe take a few more questions. Power industry has a problem, okay? LA Water and Power generates its electricity in Las Vegas because they don't care if they puke out the air in Las Vegas because Las Vegas is a place to puke. So what they do is they have this giant power line that carries it from Las Vegas to Los Angeles, which seems fine and dandy. The resistance of the line obviously is small, okay? But the problem is the power wants to flow at the speed of light, okay? Now, here's the condition that occurs. If the generators in Las Vegas are attempted to stay synchronous with the generators in Los Angeles, the problem is it takes a certain amount of time for the electromagnetic wave to propagate from Los Angeles, or from Las Vegas to Los Angeles. So now if the generator in Las Vegas is sitting at top dead center, so to speak, on one cylinder of an engine, or however you want to represent the phases, the one in Los Angeles has fallen behind by about 1/8 of a cycle. Okay, now if you get to the situation where the line is 1/4 wavelength long, a wavelength at 60 cycles is 2,880 miles. So it's kind of hard to do, but there are some power lines that are very long. So here's what has to be done. If the line gets longer, the generator at the other end becomes more and more, it's in step with what it thinks happening because the retarded potential. When they become 90 degrees apart, they can no longer stay synchronized and you get a big blast. So here's what the power company
Unless
does.
you had quantum entanglement with the two
Well,
generators,
whatever,
just-
that doesn't exist in this talk. That's denied, okay? So here's how they do it. They don't involve themselves in quantum mysticism because you can't make anything out of it that works in the electrical world. They use a very simple thing. They do what we were just talking about here. What they do is they take every 100 miles on the power line and put a capacitor in series with the power line. Now that capacitance in series with the power line sets the time angle back every time the wave is going through a capacitor station. These capacitors are gigantic. It would take 10 of these rooms to hold them. What this does is then it takes no time for the wave to go from Las Vegas to Los Angeles, and the two generators can stay in synchronism. What the power company done has made the propagation velocity through the Alexanderson and Tesla principles infinite. So there's no time delay of energy propagation. Now this is a practical example utilized by the utility companies to bring the two spatially separated items into one unit dimension in the dimension of time by neutralizing space. This is one way, this is how Tesla would transmit. He wouldn't transmit by transmitting the energy. He worked on the principle that the energy is brought into one by a mutual relationship where there is no velocity. In counter space, it's a counter velocity. The farther apart you are in counter space, the closer you are together. That's why these planets can have such a profound influence on the sun, which is going on right now. There's a big planetary alignment, and the sunspot number has been on the bottom now for, it's 22-year cycles at that zero dead point, and this will be the point in the next month which will start to rise and create all the usual havocs it does to the radio and power industry and the usual social insanities and all the things that go along with it. So I have to end there.
We're witnessing the insanity part now, as a matter of fact.
What's that?
So we're witnessing the insanity part now, as a matter of fact.
Yeah, well, unfortunately, it's also cumulative.
We have a huge capacity.